For hundreds of years, the Orion Nebula was thought of as a peaceful nest of stars, a soft, bright cloud that hung from Orion's sword. But new data from the James Webb Space Telescope has broken that picture. To the human eye, what seems calm is actually a storm zone where chaos, radiation, and gravity all meet. As stars are born in this cosmic oven, shockwaves and magnetic fields twist and turn like snakes. Young suns send out jets that are strong enough to swallow whole solar systems. This isn't just a nursery, it's also the most dangerous place in our galaxy to give birth. The first glimpse of Orion's heart. For thousands of years, travelers and stories have used the constellation Orion to find their way in the winter sky. There is a pattern in the sky that almost everyone can spot, a belt of 3 bright stars with a slight blur below it that looks like a gem hanging from a sword. For most of human history, that cloudy area could not be seen with the naked eye. Under the hunter's belt, it looked like a small dot of light to him. But that smudge turned out to be one of the strangest and most turbulent places in our galaxy. It's 1,344 light-years away from Earth, and it's where stars are being born right now. The story of our discovery begins in 1610, when Nicolas Claude Fabry de Peiresc, a French astronomer, first observed the Orion Nebula through a primitive telescope. At the time, telescopes had only recently been invented, and astronomers were still learning what they could reveal. Peiresc's note was brief but revolutionary. He described a cloudy star that defied simple categorization. To early astronomers, every object in the sky had to be either a star or a planet. But this was neither. It didn't shine with a steady point of light. It glowed, diffuse and strange, as though something were burning behind a curtain of smoke. A few decades later, in 1656, another astronomer, Christian Huygens, used a more advanced telescope to study the same patch of sky. What he saw stunned him. He wrote that the cloudy light contained a marvelous assemblage of stars, too numerous and faint to see individually without magnification. In honor of his contribution, early astronomers called it the Huygens region, a name that still refers to the bright core of the Orion Nebula today. Huygens had no way of knowing it, but he was peering into a cosmic nursery where thousands of new suns were igniting inside colossal clouds of gas and dust. As telescopes improved, so did our picture of Orion. In the 18th and 19th centuries, astronomers began using spectroscopy, splitting light into its component colors, to analyze what this glowing gas was made of. What they discovered changed astronomy forever. The Orion Nebula wasn't reflecting starlight, it was emitting it. The nebula was full of ionized hydrogen, atoms stripped of their electrons by powerful ultraviolet radiation from newly formed stars. The gas itself was glowing because it was electrified, energized, and constantly reshaped by the very stars it was helping to create. What had once looked calm was, in reality, a turbulent factory of stellar birth. By the early 20th century, astrophotography had revealed even more detail. Long exposures taken through observatory telescopes showed that the Orion Nebula wasn't a smooth cloud at all. It was full of filaments, arcs, and cavities. These were the signatures of shockwaves, radiation fronts, and gravitational collapse. Scientists realized they were looking at a stellar nursery, a term that became a staple of modern astronomy. It was the closest large-scale region where stars like our Sun were forming, offering a living laboratory for understanding how stars, and by extension, planets, come into being. The 20th century also brought the revelation of the trapezium cluster, 4 massive stars at the nebula's center, whose combined radiation outshines everything around them. These O-type giants, each tens of thousands of times brighter than the Sun, are the engines of Orion's chaos. Their energy sculpts the surrounding gas into luminous shapes and pushes shockwaves through light years of material. Even in the early photographs, you can see their fingerprints, regions of intense brightness where stellar winds have carved out cavities in the surrounding clouds. Without them, the Orion Nebula wouldn't shine. But because of them, much of its beauty exists at the edge of destruction. The secret has been further revealed by modern telescopes. Protoplanetary disks, also known as proplids, were found by the Hubble Space Telescope. These are small, disc-shaped clouds that form around young stars and glow because they are being hit by radiation from nearby big stars. It was the first time that experts had seen other solar systems when they were still very young. Later, infrared telescopes like Spitzer and Herschel saw what visible light couldn't: a group of secret protostars buried deep in the nebula's dust lanes. Each one was like a tiny boiler about to catch fire. The heartbeat of the Orion Nebula is these stars that you can't see. They are always making new things and destroying old ones. A stellar nursery like no other. The Orion Nebula is more than just a pretty spot in the sky. It is the nearest huge star-forming region to Earth, located in the Orion arm of our galaxy and some 1,344 light-years away. It's close enough for scientists to study in great detail, but far enough away that its raw power doesn't put us in danger. The nebula is more than 24 light-years across and shines like a picture of how our sun might have looked when it was young, packed with dust, surrounded by chaos, and formed by forces that would tear most matter apart. The laws of physics clash there in a way that not many places in the universe can match. The Orion Nebula lies at the heart of a much larger structure known as the Orion Molecular Cloud Complex. This sprawling region stretches hundreds of light-years across and contains enough gas and dust to form tens of thousands of stars. It includes other famous sites, like the Horsehead Nebula and Barnard's Loop, all part of the same interconnected system of gas, sculpted by gravity, radiation, and time. But the Orion Nebula itself, known to astronomers as M42, is the brightest, most energetic pocket in the entire complex. Its glow comes from hydrogen atoms ionized by massive O-type stars, making it shine even to the naked eye on a dark winter night. Unlike many nebulae that hide their activity behind thick veils of dust, Orion's relative proximity and openness give scientists a rare, unobstructed look at the entire star formation process. Inside it, giant clouds of molecular hydrogen collapse under their own gravity, forming dense knots called protostellar cores. As these cores contract, they heat up, spinning faster and pulling in more material until nuclear fusion ignites in their centers. This is the moment a star is born. And in Orion, thousands of these events are happening simultaneously. Each young star unleashes fierce stellar winds, streams of charged particles that blast away surrounding gas and shape the nebula into luminous arcs and filaments. The trapezium cluster is located in the so-called Huygens region, which is one of the most notable parts of the nebula. Along with dozens of smaller partner stars, these four main stars give off ultraviolet light that is so strong that it carves whole holes in the gas around them. Some of the most familiar designs in astrophotography are made when nearby matter is pushed into bright walls and pillars by the radiation pressure. These structures aren't fixed. They're always changing because of how energy moves between new stars and the space around them. Every picture we take of Orion shows a moment in a cosmic fight that will look very different in a few decades. Even the color of the nebula tells a story of physics in action. The pinkish-red hues come from ionized hydrogen atoms recombining with electrons, while the green and blue tones trace oxygen and nitrogen excited by ultraviolet light. Through spectroscopy, astronomers can map these emissions and infer temperatures, densities, and chemical compositions across different zones. Temperatures in the inner regions reach up to 10,000 kelvins, while the outer molecular clouds remain just a few tens of degrees above absolute zero. That staggering contrast, from nearly frozen gas to plasma hotter than the surface of the Sun, exists within a single field of view. The Orion Nebula is also a testing ground for understanding how magnetic fields influence star birth. Observations show that invisible magnetic threads weave through the cloud, guiding the flow of gas and regulating how fast regions collapse. Without them, the nebula would likely fragment into countless smaller clumps, producing far more stars in a chaotic burst. With them, the The collapse happens more slowly, allowing stars to form in waves rather than all at once. It's a cosmic feedback system. Stars form, emit radiation, push gas outward, and in doing so set the stage for the next generation of stars to form along the edges of those cleared zones. What lies beneath the glow? The Orion Nebula looks like a soft cloud glowing pink, violet, and blue below Orion's belt at first glance. But there is a much more complicated structure behind that beauty. It was made layer by layer over light years of space. Modern science has shown that the nebula is not a single smooth cloud, but a jumbled mix of thick molecular gas, ionized plasma, and shock fronts moving at very high speeds. As new stars are born at the core, their radiation and winds make these areas that cross all the time. Every filament, ripple, and bright edge you see in a telescope picture is caused by strong physical forces. For example, ultraviolet light and star winds push clouds outward, while gravity pulls clouds inward. The Orion Nebula is essentially a window into a colossal molecular cloud called Orion Molecular Cloud 1, or OMC1 for short. This is a dense reservoir of hydrogen, helium, and dust particles, the raw material from which stars are born. The outer layers of the nebula are made of ionized hydrogen, H2, glowing brightly because of ultraviolet radiation from the trapezium cluster. These high-energy photons strip electrons off hydrogen atoms, creating a region of plasma that emits visible light. Deeper inside lies a colder, darker zone of molecular hydrogen, H2, carbon monoxide, and dust grains. This area is opaque to visible light, but shines in infrared, which is why telescopes like Spitzer and JWST are crucial for studying what lies within. Between these layers is a sharp transition boundary known as an ionization front. It's here that the real drama unfolds, where hot ionized gas meets cool molecular gas. This boundary is constantly being pushed, eroded, and reshaped by radiation pressure from massive stars. As the hot gas expands outward, it compresses the cooler material beyond, sometimes triggering new waves of star formation. The entire structure is in motion, a dynamic system of feedback where energy from one generation of stars seeds the birth of the next. The balance between creation and destruction plays out on a scale that spans dozens of light years. Within the nebula, astronomers have identified complex filaments, bubbles, and cavities formed by supersonic winds. These winds can reach speeds of over 1,000 kilometers per second, sculpting the surrounding gas into intricate shapes. Observations from the Hubble Space Telescope show pillars and arcs resembling the famous Pillars of Creation in the Eagle Nebula, though smaller in scale. Each of these formations acts as a miniature laboratory where physical processes, turbulence, shock heating, and magnetic confinement, can be studied in unprecedented detail. The interplay of light and shadow across these regions tells scientists where matter is dense, where it's moving, and how energy flows through the nebula. The glow itself is also a diagnostic tool. The Orion Nebula emits light in specific wavelengths: the bright red of hydrogen alpha, the green of doubly ionized oxygen, and the blue of helium. These emission lines allow astronomers to measure temperature, pressure, and chemical composition. The temperatures in the glowing ionized regions hover around 10,000 kelvins, while the dense molecular cores can be as cold as 20 kelvins, just above absolute zero. That extreme temperature contrast creates pressure gradients that drive turbulence throughout the cloud. The result is a constant churning motion, a cosmic storm that never truly settles. The depth of the Orion Nebula is one of the most important things scientists have learned about its structure. Many years ago, people thought it was a flat sheet of gas, but using parallax data from the Gaia mission to make a three-dimensional picture has shown a layered, almost cavernous shape, like a hollow bubble cut into a thick cloud. We're looking into that hole from the outside and can see the lit walls inside. The Orion Nebula is basically the visible part of a much bigger and darker structure that extends behind it. It is the open side of a huge star nursery. This is why the nebula looks so bright even though it's not very big. We're looking straight into an area that is charged from the inside. Dust plays a critical role in shaping what we see. These tiny particles, silicates, carbon compounds, and frozen ices, absorb and scatter light, creating dark lanes and shadows across the nebula's face. Yet dust also protects fragile molecular regions from harsh radiation, allowing new stars to form. In many images, you can see streaks where dust absorbs starlight, tracing the paths of dense filaments that may be collapsing into future suns. Without dust, the nebula would quickly evaporate under the glare of the trapezium stars. With it, a delicate balance is maintained, one that ensures both destruction and creation continue side by side. Gravitationally, the nebula is a web of interactions. Each forming star pulls on the surrounding material, altering the flow of gas and shaping new filaments. Clusters of young stars create local gravity wells that guide how nearby matter collapses. Meanwhile, radiation pressure from massive O-type stars counters that pull, blowing cavities into the surrounding gas. This tug-of-war between gravity and radiation defines the nebula's architecture. Over millions of years, these processes will hollow out the cloud entirely, leaving behind a naked cluster of young stars surrounded by a faint shell of leftover gas, the last trace of a once glowing birthplace. The trapezium cluster. In the middle of the Orion Nebula, there is a group of stars that are so bright that they can see almost everything else. This is the trapezium cluster, a small but very strong group that determines the form, color, and energy of the whole nebula. The cluster is named after the way its four brightest stars are arranged in a trapezoid shape. It is in the Huygens region of the nebula, which is the hot core that lights up the clouds around it. Astronomers see these stars as the engines of one of the most busy, star-forming regions in the Milky Way. To the human eye, they look like a tight, sparkling cluster. The cluster's four central stars, Theta 1 Orionis A, B, C, and D, are young, massive, and unstable. Together, they're less than 2 million years old, practically newborns by cosmic standards. The most dominant of them, Theta 1 Orionis C, is an O-type star roughly 40 times the mass of the Sun and 200,000 times more luminous. It alone produces most of the ultraviolet radiation that ionizes the surrounding gas, creating the nebula's vivid glow. The others, while smaller, still dwarf the Sun in size and energy output. They form a gravitationally bound system, orbiting one another in complex, unstable loops, a cosmic dance that may one day fling some of them into interstellar space. The trapezium cluster is not just four stars. Surrounding them are hundreds of smaller stars and protostars, some visible only in infrared light. These young suns range from massive B-type stars to tiny brown dwarfs, failed stars that never reached fusion temperature. Together, they make up the Orion Nebula cluster, an extended family of more than 2,000 members, all born from the same molecular cloud. Yet, it's the four central O-type stars that act as the nebula's sculptors, their radiation and stellar winds shaping everything within dozens of light years. You are unable to comprehend how strong those star winds are. At millions of kilometers per hour, streams of charged particles shoot out into space and hit gas and dust close. These winds make holes and shock fronts in the material around them, sending it into bright arcs and pillars. When we look at pictures of Orion's complicated shapes, its fuzzy edges, bright filaments and dark lanes, we are seeing work that was done by the trapezium cluster. This is a real-life example of stellar feedback, which is how big stars changed the place where they were born. The nebula would stay thick and cloudy without these winds. When they are there, it turns into a bright canvas of charged gas. The radiation from these stars also creates one of the most extreme environments for planetary formation in the galaxy. Around many of the smaller stars in the cluster, astronomers have detected protoplanetary disks, or proplids. These are the seeds of future solar systems, disks of dust and gas orbiting young stars. However, in the heart of Orion, they're constantly bombarded by intense ultraviolet light. The outer layers of these disks are heated, ionized, and stripped away in a process known as photoevaporation. It's a brutal test for early planet formation. only the densest disks survive long enough to form solid worlds. Those that do will bear the scars of their violent beginnings. When astronomers first imaged these proplids using the Hubble Space Telescope in the 1990s, it was a revelation. Dozens of comet-shaped disks appeared around the trapezium cluster's smaller stars, their tails pointing away from Theta 1 Orionis C. Each one was a miniature world builder fighting to survive in a storm of radiation. Some of these disks have bright central stars and dark silhouettes, while others glow faintly as they're heated from within. They represent every possible stage of planetary genesis, from collapsing gas clouds to developing systems that might one day resemble our own solar neighborhood. The gravitational dynamics inside the trapezium cluster are equally chaotic. Because these stars are packed so closely together, their orbits constantly change due to mutual gravitational tugging. Encounters between stars can fling smaller members outward at tremendous speeds, sometimes fast enough to escape the cluster entirely. These runaway stars have been detected streaking away from Orion, traveling at velocities of up to 100 kilometers per second. Their trajectories trace back directly to the trapezium, suggesting that violent gravitational slingshots occur frequently in this stellar arena. Each ejection carries with it the potential to see distant parts of the galaxy with heavy elements forged in Orion's furnace. Starbirth under fire. The Orion Nebula is not a calm place where stars quietly light up. It's a battleground. There is a lot of chaos around every star that forms here. There is radiation, magnetic storms, and fast winds that tear through the gas like shockwaves. To fully understand starbirth in Orion, picture a scene that is constantly violent, with clouds falling, jets bursting outward, and radiation from nearby giants threatening to destroy new stars before they can even settle down. There is both growth and destruction going on at the same time, on a size so big that light takes years to cross the battlefield. Star formation in Orion begins deep within the nebula's dense molecular clouds, where gravity slowly pulls together cold hydrogen gas and dust. Over tens of thousands of years, these collapsing regions, called protostellar cores, grow denser and hotter. When temperatures in the core reach about 2000 kelvins, the hydrogen molecules begin to break apart, releasing energy that accelerates the collapse even further. Eventually, as the core's temperature climbs past 10 million kelvins, nuclear fusion ignites. A new star is born. But in Orion, that's only the beginning of its struggle for survival. The moment a protostar ignites, it starts interacting violently with its environment. The energy released from its growing nuclear core drives powerful outflows, streams of ionized gas that blast through the surrounding cloud. These bipolar jets can stretch for light years, slamming into surrounding gas and creating glowing shock fronts known as Herbig-Haro objects. Each one marks a collision point where matter moving at hundreds of kilometers per second meets dense gas, lighting it up like a cosmic flare. In Orion, hundreds of these can be found scattered across the nebula, each one tracing the path of a young star fighting its way free from the womb of dust. The star's magnetic field also plays a crucial role in this violent birth. As the collapsing gas spins faster, thanks to the conservation of angular momentum, it forms an accretion disk around the protostar. Material spirals inward through this disk, feeding the growing young star, while magnetic lines channel some of it into jets that shoot out from the poles. This process helps regulate the star's growth. Too much in falling matter, and the star could collapse under its own weight. Too little, and fusion might never stabilize. In Orion, this balance is made even more precarious by the external pressure of ultraviolet radiation and stellar winds from the nearby trapezium cluster. Those winds and radiation act like an unrelenting storm. They strip away gas, scatter dust, and create cavities in the surrounding molecular cloud. Some protostars manage to shield themselves within dense cocoons, protected from the worst of the radiation. Others aren't as lucky. Their disks get photo-evaporated before planets can form, leaving only bare stars adrift in glowing plasma. This is one reason why astronomers believe the Orion Nebula is an inefficient nursery. For every star that survives, many potential ones are extinguished before birth, torn apart by the forces unleashed by their massive neighbors. The same destructive forces can also spark new creation. As shockwaves and radiation fronts push through the nebula, they compress nearby regions of gas, causing them to collapse and form new stars. It's a cycle of death giving way to birth, each generation of massive stars seeding the next. Observations from the Hubble and Spitzer space telescopes have shown chains of such triggered star formation running outward from the nebula's center, like ripples on a pond. Each wave marks an older generation of stars clearing the path for the next. Orion is, in essence, a stellar production line powered by violence. Infrared observations from the James Webb Space Telescope have added an even more dramatic layer to this picture. Webb's sensitivity has revealed hundreds of hidden protostars embedded deep in the nebula's dust lanes, many of them in their earlier stages of development. These objects emit faint heat signatures rather than visible light, their surfaces still too cool to glow brightly. Around many of them, JWST has detected complex outflows, tangled magnetic fields, and arcs of compressed gas that show where stellar winds collide. Some of these protostars are less than a few thousand years old, making them some of the youngest ever observed in the Milky Way. A place in Orion called Orion BNKL, Becklin-Neugebauer-Kleinman-Low, is one of the most dangerous. It is where rapid star formation happens and is hidden in the thick OMC-1 cloud. Infrared images and radio data show that a terrible event happened here about 500 years ago. Several stars collided, sending huge objects flying outward at very high speeds. The pieces of that event are still growing, going through the gas around it, and leaving behind shock fronts that glow in infrared light. It's a warning that chaos rules even when stars are being born. Close calls between huge protostars can change the shape of whole areas of space. Proplyds, the solar systems in progress. In the Orion Nebula, where the winds are strong and the light is very bright, a quiet wonder is happening. Possible planetary systems are being born. Proplyds, which stands for protoplanetary disks, is what astronomers call them. They are flattened clouds of gas and dust that circle young stars. They spin slowly as gravity and angular momentum shape them into the first shapes of solar systems to come. Seeing them is like seeing how the universe has changed over time. And Orion is the only place in the Milky Way where there are more of them or more threats to their survival. Before the 1990s, astronomers suspected that disks might form around new stars, but direct evidence was rare. Then came the Hubble Space Telescope. In 1994, its instruments captured astonishing images of the Orion Nebula that changed our understanding of planetary formation forever. Dozens of teardrop-shaped silhouettes appeared against the nebula's glowing background, dark disks with bright central stars surrounded by comet-like halos. These were the proplyds, and they were everywhere. Each one represented a snapshot of what our own solar system might have looked like over 4 billion years ago, a swirling, dusty nursery on the edge of ignition. A typical proplyd in Orion spans about 100 astronomical units across, roughly twice the width of our solar system, and contains enough raw material to form planets, moons, and asteroids. The disks are made primarily of hydrogen and helium, mixed with heavier elements like carbon, silicon, and oxygen, along with microscopic grains of ice and dust. As the disk spins, material gradually clumps together. Tiny grains collide and stick, forming pebbles, then rocks, then planetesimals, the building blocks of planets. In the densest parts of these disks, heat and pressure may already be forming proto-Jupiters or rocky worlds. But life in Orion's proplyds is anything but easy. They exist in the harshest possible environment for planetary construction. The trapezium cluster's O-type stars flood the region with ultraviolet radiation thousands of times stronger than what reaches Earth from our Sun. This radiation heats and ionizes the upper layers of each disk, blowing away gas and dust in great comet-like tails. The process, known as photoevaporation, can strip a proplyd of its outer material in just a few 100,000 years, a blink of an eye in cosmic time. Only the densest and most compact disks can survive long enough to form fully fledged planets. This discovery forced astronomers to rethink what kind of environments are truly friendly to planet formation. In peaceful, isolated regions like the Taurus molecular cloud, protoplanetary disks can evolve undisturbed for millions of years. But in Orion's intense radiation fields, planetary formation is a race against destruction. Observations suggest that while hundreds of disks may form here, only a fraction will last long enough to build stable systems. Yet those that do will likely give rise to rugged, tightly bound planets. Worlds forged in fire, with dense atmospheres and high metal cores. Even in the face of such hostility, the Orion Proplyds are remarkably diverse. Some appear as glowing bubbles, their surfaces illuminated by nearby stars. Others are dark, silhouetted against the bright nebula background, dense enough to block visible light entirely. Many show long, curved tails pointing directly away from Theta 1 Orionis C, evidence of the fierce radiation wind sculpting them. The variety reflects different stages of evolution. Some disks are still thick and opaque, others have already been eroded into delicate arcs and wisps. Together they form a kind of cosmic time-lapse, capturing every stage of early solar system development in one region. Infrared and radio observations have revealed even more hidden detail. Using the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, astronomers have mapped the chemical makeup of several Orion Proplyds in exquisite resolution. They've detected traces of water vapor, carbon monoxide, and complex organic molecules, ingredients essential for life. In a few of the most massive disks, ALMA has even identified concentric rings and gaps, hinting at the presence of forming planets sweeping up material along their orbits. These observations suggest that despite the odds, full planetary systems are emerging inside the nebula's fiery core. We can also figure out what will happen to these disks by looking at their shapes. The ends of the proplyds closest to the trapezium cluster are severely cut off, which shows that they have been heavily worn away. From farther away, where radiation is weaker, the rings look fuller and rounded. Astronomers can study how outside forces change young planetary systems in a way that can't be done anywhere else. You could say that the Orion Nebula is home to every experiment that nature can do, from fully guarded disks in calm zones to half-destroyed survivors in the storm. The hidden violence of ultraviolet light. It would be ultraviolet light if the Orion Nebula had a secret weapon. This radiation is so strong that humans can't see it, but it fills the nebula and kills everything it touches by taking electrons from atoms, turning gas into vapor, and changing the shape of everything it touches. Its ethereal beauty comes from the bright reds and greens that can be seen through telescopes. However, this is also what makes it one of the worst places in the galaxy for new stars and planets to form. The main ones are the big O-type stars in the trapezium cluster, especially Theta 1 Orionis C. Their UV light is so strong that it can cook whole disks of gas and dust, which is exactly what planets need to form, even at great distances, several light years. To understand this violence, imagine standing near a blast furnace large enough to engulf the solar system. The ultraviolet light streaming from the trapezium doesn't just illuminate the surrounding gas, it ionizes it. Hydrogen atoms lose their electrons, transforming into plasma that glows vividly in visible light. This is what makes the Orion Nebula shine, but it comes at a price. Every photon of ultraviolet energy carries the potential to destroy complex molecules, disintegrate ice grains, and break apart fragile dust clusters that would otherwise combine into planets. In short, the same radiation that gives birth to light destroys the building blocks of life. Astronomers studying the proplyds have seen this process in action. The disks closest to the trapezium stars are literally boiling away. Intense ultraviolet light heats their upper layers to thousands of degrees, driving gas out in long, comet-like tails. This photoevaporation creates striking shapes, bright heads and streaming arcs that always point away from the radiation source. Observations show that the rate of mass loss in these exposed disks can reach up to 100 million tons per second, Within just a few 100,000 years, an entire protoplanetary disk can vanish, its gas stripped away long before planets can take form. Infrared and X-ray observations have revealed that the ultraviolet radiation doesn't just cause evaporation, it triggers shockwaves. As the heated gas expands outward, it collides with cooler, denser material around it, creating regions of compression that glow intensely in emission lines of hydrogen and oxygen. These shock fronts are like cosmic walls of fire, marking the boundaries where destruction meets creation. They can compress nearby gas enough to ignite new bursts of star formation, making ultraviolet light both a destroyer and a creator, a paradox that defines the Orion Nebula's life cycle. The chemistry inside the nebula is also rewritten by ultraviolet exposure. Normally, molecular hydrogen, H2, dominates cold clouds, but in Orion, ultraviolet light tears it apart, forming a photodissociation region or PDR, where atomic hydrogen and ions coexist in a turbulent equilibrium. Here, carbon monoxide is broken into carbon and oxygen, ices are vaporized, and complex organic molecules are shattered into fragments. Yet at the same time, ultraviolet photons drive new reactions, creating exotic molecules like hydroxyl, OH, and ionized carbon, C+. The Orion bar, a dense ridge where ultraviolet light meets cold gas, is one of the best-known PDRs in the universe, a living boundary between radiation and molecular stability. Even deeper in the nebula, ultraviolet light influences the evolution of stars themselves. It shapes the accretion disks around young suns, setting limits on how much material they can draw in. Stars exposed to too much radiation tend to stop growing earlier, becoming smaller and cooler than their isolated counterparts. This means the environment of Orion doesn't just sculpt planets, it determines the final masses of stars. The radiation acts like a cosmic regulator, ensuring that no single star can consume all the gas around it before others have a chance to form. Ironically, the same destructive energy that tears apart disks helps maintain the nebula's balance. When you think about how powerful our Sun is, this ultraviolet light is truly amazing. Theta 1 Orionis C gives off more than 100,000 times as much UV light, which is enough to ionize gas in an area 20 light-years across. Getting Earth into the Orion Nebula would be impossible. Its atmosphere would be gone in seconds, and the seas would boil from the constant pressure. Even spaceships with current heat shielding would fall apart in a matter of seconds. From far away, the nebula looks beautiful, but it hides a place where life as we know it would not survive at all. Supersonic outflows and Herbig-Haro objects. There is a kind of mark that every new star in the Orion Nebula has, plasma jets that shoot out from its poles at hundreds of kilometers per second. These rapid streams are some of the most amazing things that can happen in the universe, and they show how rough it really is for stars to form. When these jets hit the thick gas around them, they send out bright shock waves called Herbig-Haro objects. They were named after the scientists George Herbig and Guillermo Haro, who studied them in the 1950s. There are hundreds of these glowing knots spread out across the nebula in Orion. Each one marks the beginning of a young, nervous star that is still trying to find its place in the universe. To the eye of a telescope, a Herbig-Haro object looks like a small patch of blue or orange light, often shaped like a bow or fan. But those gentle colors mask violent motion. The plasma jets that produce them travel at speeds up to 400 kilometers per second, fast enough to cross the distance between Earth and the Moon in just 15 minutes. When this material slams into nearby gas and dust, it compresses and heats the impact zone to thousands of degrees, causing atoms to glow. The shock waves ripple outward, illuminating trails that stretch for light years. Each glowing filament you see in Orion's deep space images is essentially a scar left by one of these high-speed collisions. These outflows are the natural byproduct of star formation. As a protostar forms inside a collapsing cloud, material falls inward through an accretion disk, spiraling toward the growing core. But not all of that material stays. some is redirected along the star's magnetic field lines and ejected outward from the poles. The result is a pair of jets shooting in opposite directions, often aligned so perfectly that they form symmetrical patterns across space. This process helps the young star shed angular momentum, preventing it from spinning itself apart. In effect, these jets are how a forming star maintains balance by ejecting part of itself into the void. Orion is one of the richest laboratories for studying these outflows because it's young, active, and close enough for detailed imaging. Many of its Herbig-Haro objects, like HH1, HH2, and HH212, are considered textbook examples. HH212, for instance, is a stunning twin-jet system extending from a protostar deep within the Orion molecular cloud. The jets emerge as narrow beams of plasma, each nearly a light-year long, with glowing knots that trace the rhythm of the young star's eruptions. Every few years, the protostar expels a new burst of material, sending a ripple through the jet like a heartbeat of creation. Infrared telescopes, like the James Webb Space Telescope and Spitzer, have revealed that many of these jets are embedded deep within dusty cocoons, invisible in optical light. Webb's infrared view penetrates the dust, showing structures that look like cosmic fountains, collimated streams of hot gas carving tunnels through the molecular cloud. Some of these tunnels intersect, forming complex webs where multiple young stars are shaping the same environment simultaneously. The result is a chaotic network of shocks and cavities, with new Herbig-Haro objects constantly appearing as others fade away. The Orion Nebula, in this sense, is not static. It's alive, flickering with eruptions that can change the view from decade to decade. When these supersonic jets collide with gas that's already been ionized by the trapezium cluster's ultraviolet radiation, the results are even more dramatic. The glowing arcs become sharper, brighter, and more structured, producing the spectacular wisps seen in photographs of the nebula's inner regions. Observations show that some jets interact directly with neighboring outflows, twisting or deflecting each other in mid-flight. These collisions can trigger additional waves of turbulence, compressing gas in new regions and sparking yet another generation of star formation. It's a chain reaction of violence and creation, all unfolding in real time. The Herbig-Haro objects also serve as natural clocks. By measuring their speeds and directions, astronomers can calculate how old the associated stars are. Most of Orion's visible Herbig-Haro objects are just a few thousand years old, meaning their parent stars are still in the earlier stages of development. In some cases, you can trace a single jet back to its source, revealing a deeply embedded protostar hidden behind a veil of dust. The fact that these young stars produce such powerful outflows tells us that even at their infancy, stars exert enormous influence over their surroundings. As these jets shoot outward, they create turbulence that can cause nearby groups of gas to break, which is a lot like planting a seed for a new star. This is how the confusion that one generation makes feeds the next. In the inner parts of Orion, there are many of these kinds of feedback loops where new stars kill old ones and make room for new ones to form at the same time. The nebula will continue to shine for millions of years because it is a never-ending circle. Molecular mayhem. Under the bright surface of the Orion Nebula is a world in chaos. A thick jungle of gas and magnetic energy where the building blocks of stars are constantly being torn apart, reborn, and squeezed. This area is known as the molecular cloud zone by astronomers, and it's where the real chaos of creation takes place. This layer is cold, dark, and not visible to visual light, unlike the bright charged surface that telescopes see. Still, it holds the huge amount of hydrogen, carbon monoxide, and dust that the next generation of stars will be born from. The cloud that can be seen is like a flame, and the molecular zone is like the fuel that keeps it going. This region, officially known as Orion Molecular Cloud 1, OMC1, stretches for more than a dozen light-years and hides structures so dense that light can't escape. Here, gravity competes with turbulence in a constant tug-of-war. Massive filaments of gas twist and coil, sometimes collapsing under their own weight, sometimes torn apart by external pressure. Within these filaments, pockets of gas, each many times the mass of the Sun, condense into clumps that will eventually ignite as new stars. It's an environment of delicate instability. Even a small shockwave from a neighboring explosion can tip the balance between creation and dispersal. But OMC-1 is not a quiet laboratory. It's one of the most active and violent regions ever observed in the Milky Way. Observations across multiple wavelengths, from radio to infrared to X-ray, reveal intense turbulent motion, where gas clouds move at speeds of tens of kilometers per second. The cause of this turbulence is twofold: the fierce radiation and stellar winds from the trapezium cluster pushing inward, and the eruptions from newly formed stars deep within the cloud pushing outward. Together, they create a maelstrom of colliding flows, shock fronts, and magnetic shearing that keeps the cloud in a constant state of agitation. This chaos is not just noise, it's the mechanism by which stars are born. In a calm environment, gas would simply drift, never compressing enough to form stars. But in a turbulent one, shock waves act like cosmic pistons, forcing gas into dense knots. These compressed regions collapse rapidly, producing bursts of star formation known as stellar clusters. In Orion, astronomers can see this process in real time. Some areas of the cloud show distinct signs of recent compression, sharp ridges of glowing gas, and sudden jumps in temperature that mark where shock fronts have passed. These are the fingerprints of turbulence-driven creation. The molecular chemistry of OMC-1 adds another layer to this mayhem. Inside these cold regions, molecules constantly collide, stick, and break apart. Observations by the Atacama Large Millimeter Submillimeter Array, ALMA, have identified more than 60 different molecules here, including ammonia, formaldehyde, methanol, and even complex organic compounds. Many of these form on the surfaces of dust grains, which act like microscopic chemical reactors. When shock waves or ultraviolet photons hit these grains, the molecules are released into space, enriching the cloud's chemistry. Over time, these same compounds may become the seeds of planetary atmospheres, comets, or even the building blocks of life. The Orion BNKL outflow, a huge explosion of molecular gas that happened about 500 years ago, is one of the most fascinating finds that has been found in this turbulent zone. Astronomers think it was caused by a strong gravitational pull between a group of young, huge stars. When these protostars got too close to each other, they shot apart at very high speeds, some going over 100 kilometers per second, and released a huge amount of energy that sent gas jets flying everywhere. These outflows are now more than a light year across and are still growing. They are shining infrared light on the clouds around them. The BNKL outflow is a great example of molecular mayhem, which is when forces so strong that stars themselves become missiles collide. The magnetic fields running through the Orion molecular cloud add yet another dimension of complexity. Invisible but immensely powerful, they thread through the gas like twisted cables, influencing how material moves and collapses. When gas flows along these magnetic lines, it forms elongated filaments, the structures seen in infrared images as wisps and tendrils. If the magnetic tension becomes too strong, it can resist gravitational collapse, halting star formation locally. But when the field lines are disrupted by turbulence or shock waves, the resistance breaks down and gravity takes over. In this way, magnetic fields act as both barriers and catalysts, controlling the rhythm of Orion's stellar evolution. In this setting, sound, actually pressure waves, play a part. Even though space is almost empty, the dense molecular gas in Orion is thick enough that changes in pressure can move through it. This is known as acoustic turbulence by scientists. These low-frequency waves move at several kilometers per second and send energy across the cloud, where they change the flow of motion and heat. Furthermore, they help to keep the matter moving, making sure that no part of the cloud stays still. If someone could hear better than humans, the depths of Orion would not be quiet. They would be filled with the sounds of gas falling and shock waves from far away. The Orion bar, The Orion bar is a bright, knife-like structure that forms one of the most interesting edges in the galaxy. It is at the edge of the Orion Nebula's glowing heart. Two very different worlds meet at this narrow line of light that runs along the southeast edge of the nebula. On one side is the hot, charged gas that is soaked in ultraviolet light from the trapezium cluster. On the other hand, cold molecular hydrogen hides in the dark, ready to break apart into new stars. There is a line between them called the Orion bar. This is where energy, matter, and chemistry meet in a violent balance that makes the nebula stand out. To the eye of a telescope, the Orion bar looks like a glowing wall, sharply defined and brightly illuminated. But to scientists, it's far more than a boundary. It's a photodissociation region, PDR, an area where ultraviolet photons from massive stars strike the surface of a molecular cloud, stripping electrons, breaking bonds, and heating the gas layer by layer. The bar is, in effect, a cosmic laboratory, where the universe performs its most fundamental chemical experiments. It's only about 1 light-year thick, but within that thin sheet, temperatures can swing from nearly 10,000 kelvins in the exposed layer to less than 100 in the shadowed core. A contrast so extreme, it could vaporize any solid matter in seconds. This razor-thin interface is what makes the Orion bar such a treasure for astronomers. Every molecule, atom, and grain of dust crossing that boundary undergoes a transformation. Ultraviolet light breaks molecular hydrogen, H2, into individual atoms. Carbon monoxide, ammonia, and complex hydrocarbons are torn apart, creating a layer dominated by ionized carbon, C+, oxygen, and free electrons. Just a few hundred billionths of a meter below the surface, shielded by a thin veil of dust, molecules begin to reform again. It's a constant cycle of destruction and creation, all playing out across a transition zone that telescopes can now map in extraordinary detail. The Orion bar also acts as a natural amplifier of light. Because it's viewed edge-on from Earth, we're essentially looking through a long column of glowing gas, making it appear far brighter than it would face on. This geometry allows astronomers to measure how radiation penetrates molecular clouds, a key question in astrophysics. Observations from instruments like the Very Large Telescope, VLT, ALMA, and the James Webb Space Telescope have revealed a layered structure with remarkable precision. Each chemical species, ionized carbon, atomic oxygen, molecular hydrogen, emits light at different wavelengths, forming distinct stripes that trace how deep the ultraviolet radiation penetrates. It's one of the clearest examples in the universe of how starlight sculpts matter. The bar's magnetic fields add even more complexity. Polarization measurements show that magnetic lines run parallel to the ridge, confining the gas and influencing how heat and radiation spread through it. These fields help stabilize the boundary, preventing it from collapsing under pressure differences. But they also channel energy, creating narrow filaments where gas flows faster and denser clumps form. Some of these dense knots may eventually collapse into new stars once the pressure from radiation weakens. The Orion bar, therefore, isn't just a border. It's a birthplace waiting for its next wave of ignition. Dust grains within the bar play a vital role as well. Coated with ices of water, methane, and ammonia, these microscopic particles absorb ultraviolet light and re-emit it as infrared radiation, acting as tiny energy converters. When the radiation becomes too strong, the ices evaporate, releasing molecules back into the gas phase. This constant exchange between dust and gas drives the nebula's chemical evolution. The James Webb Space Telescope has detected signatures of polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules, glowing along the bar's surface. These compounds are of particular interest because they're considered precursors to the organic chemistry that underlies life. In Orion, they form and are destroyed in a continuous loop, showing how even in violent places, the building blocks of biology can emerge. One thing that stands out about the Orion bar is how lively it is. Photos may make it look like it doesn't change, but studies made over the last few decades show that it is actually moving and changing shape all the time. The bar moves back and forth, sending compression waves deeper into the molecular cloud as the stellar winds from the trapezium stars change. Along the edge, these waves can cause new stars to form, making birth ripples that spread out like rings in a pond. In a sense, the Orion bar is like a rolling shock front where radiation pressure and gravity are always fighting with each other. The dark nebula within. Behind the bright surface of the Orion Nebula is an area that has been so thick, cold, and hidden for hundreds of years that no one has been able to see it. Scientists call it the dark nebula within because it is the heart of the Orion molecular cloud, one that is hidden from view. With the naked eye, it looks like a hole, a black spot behind the bright cloud of gas that stars. Molecular hydrogen, carbon monoxide, and dust make up a huge boiling mass that is hundreds of times denser than the Sun and silently breaking into new stars. This is what infrared and radio telescopes show. This is where the real story of how Orion was made is happening, but it's not in the light. In visible light, the dark nebula is completely opaque. Dust grains suspended in the gas absorb and scatter photons, blocking almost all radiation from escaping. The only way to see through it is by shifting into longer wavelengths, infrared, submillimeter, and radio, where light can slip between the grains. When astronomers first turned such instruments toward Orion, they were stunned. What appeared to be an empty void in optical telescopes was, in fact, teeming with energy. Buried inside were dozens of protostars, swirling disks, and jets. An entire hidden ecosystem of stellar birth concealed beneath the bright facade of the nebula. Temperatures in this region plunged to as low as 20 kelvins, only a few degrees above absolute zero. At such extremes, gases condense into thick filaments that thread through the cloud like frozen rivers. Gravity slowly pulls material along these filaments into dense knots, where the first sparks of nuclear fusion will soon ignite. Each knot represents a star in waiting, still invisible, still cocooned in dust. These forming stars are so young that their cores haven't yet reached fusion temperatures. Instead, they shine faintly in infrared light as they gather mass from their surroundings. Observations by the James Webb Space Telescope have revealed hundreds of these hidden embryos, glowing like embers inside a coal-black fog. The OMC-1 core is also home to one of the most dramatic events in the entire Orion Nebula, the BNKL explosion, named for the Becklin-Neugebauer and Kleinman-Low infrared sources. Roughly 500 years ago, several massive young stars in this region appear to have collided or passed dangerously close to each other. The resulting gravitational slingshot flung them outward at incredible speeds, some moving over 100 kilometers per second, while simultaneously releasing a titanic burst of energy that tore through the surrounding gas. Today, astronomers can still trace the blast's aftermath, high-speed molecular bullets radiating outward in all directions, glowing in infrared and radio wavelengths. Each one is a fragment of gas hurled into space by an event powerful enough to reshape an entire section of the nebula. This outburst left its mark not only in motion, but also in chemistry. Shockwaves from the explosion heated the surrounding gas, triggering new reactions and forging complex molecules. Observations have detected ammonia, formaldehyde, sulfur dioxide, and even methanol, all byproducts of high-energy collisions. As the shock fronts expanded, they compressed nearby regions of the cloud, potentially triggering the next wave of star formation. In this sense, the dark nebula isn't just a graveyard of hidden material, it's a factory of creation, using its own destruction to fuel new beginnings. The web of magnetic fields inside the OMC-1 core is one of the most interesting things about it. Even though you can't see them, these areas hold the cloud together. Using polarized light-sensitive instruments, scientists have found that magnetic lines run through the dark nebula in a planned way. These lines control the flow of gas and the rate of collapse. When the fields are strong, star formation slows down. When they are weak, gravity takes over, and groups of protostars appear. This magnetic dance gives order to what would otherwise be complete chaos. There is order beneath the confusion. Dust plays an equally vital role. Though often described as an obstacle, it's actually a shield that makes star formation possible. Dust grains protect fragile molecules from being destroyed by ultraviolet radiation, allowing the gas to cool and condense. On their surfaces, atoms stick together and form new compounds: water, methane, carbon dioxide, the same ices that will later become part of comets and planets. As the young stars heat up, these ices sublimate, releasing their chemical cargo into the surrounding space. This constant recycling of matter is what gives Orion its extraordinary richness in organic molecules. Infrared images from telescopes like Spitzer, Sophia, and now JWST show that the dark nebula is not a uniform block of gas, but a layered landscape. There are cavities carved by jets, filaments glowing faintly in infrared, and dense cores where new suns are about to ignite. In some areas, protostellar outflows have already punched holes through the cloud, sending material streaming outward like miniature volcanoes. Each outflow injects energy into the surrounding gas, preventing it from collapsing too quickly and allowing new stars to form in neighboring regions. Infrared eyes, what Spitzer and JWST revealed. When scientists directed the Spitzer Space Telescope at the Orion Nebula for the first time, they saw a sight of fire and smoke that had never been seen before. Infrared light turned the bright colors of visible light into streams of glowing gas, coiling filaments, and groups of stars that couldn't be seen. Spitzer showed what humans had seen as a calm cloud to be an ocean of heat that was moving around. There was energy hiding beneath the dust, and every swirl, pillar, and bright knot turned out to be a sign of it. That was just the start. 20 years later, the James Webb Space Telescope, JWST, would go back to the same area and find features that were so small and dense that they changed the whole way scientists think about how stars form. Infrared light has one crucial advantage in a place like Orion. It can pass through dust that blocks visible light. Where optical telescopes see only darkness, infrared instruments see heat radiating from stars, disks, and even the smallest grains of dust. Spitzer's detectors, sensitive from 3 to 180 microns, penetrated deep into the Orion molecular cloud, revealing hundreds of newborn stars previously unknown. Many of them were still cocooned inside their birth clouds, invisible to Hubble's optical cameras. What Spitzer found was a region far more crowded and chaotic than anyone expected. A swarm of young suns, glowing filaments of dust heated by radiation, and shockwaves from jets and winds colliding with the surrounding gas. Spitzer also transformed our understanding of protoplanetary disks. By measuring the infrared light emitted from these disks, astronomers could determine their composition and temperature. They found evidence of silicate dust, ices, and carbon-rich compounds, materials that resembled the building blocks of planets in our own solar system. In some disks, Spitzer detected warm water vapor and traces of complex organics like acetylene and hydrogen cyanide. These findings confirmed that the chemistry of life can emerge even in places dominated by intense radiation and turbulence. The Orion Nebula, it seemed, was not just a star factory. It was a chemical crucible. Then, in 2022, the James Webb Space Telescope took that revolution to the next level. Armed with its near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, JWST looked into Orion with a level of resolution that made even Hubble seem blind by comparison. Where Hubble could detect hundreds of stars, Webb revealed thousands. Where Spitzer saw glowing filaments, Webb resolved them into networks of fine threads and knots, each corresponding to shock fronts, jets, or dense clumps of gas. Its images showed the nebula in layers, each color corresponding to different molecules: hydrogen glowing red, carbon monoxide shimmering orange, and polycyclic aromatic hydrocarbons, complex carbon chains, shining teal across the ridges. In the Orion bar, JWST exposed an astonishing level of detail. It captured how ultraviolet light from the trapezium stars penetrates the surface, heating dust grains and evaporating ices in real time. For the first time, scientists could see where atomic hydrogen becomes molecular hydrogen, the exact point where matter transitions from chaos to creation. In one narrow slice of this interface, Webb detected more than 100 distinct chemical species, including carbon dioxide, methane, and water ice, all coexisting within a single light-year of space. This thin zone, previously hidden, is now recognized as one of the most chemically complex environments ever observed outside our solar system. Infrared spectroscopy from Webb also gave astronomers an unprecedented look at the BNKL explosion region. Using its instruments, researchers traced the molecular bullets of gas streaming outward from the 500-year-old outburst. Each bullet is a clump of gas roughly the size of our solar system, traveling at speeds up to 150 kilometers per second. Webb's data showed that these clumps are rich in silicon monoxide and iron, signs of high-temperature shock chemistry. In effect, JWST has turned the Orion Nebula into a time-lapse movie of a cosmic explosion, letting scientists watch the lingering echoes of a stellar collision that reshaped the region centuries ago. The fact that there are so many secret stars may be the most significant discovery that these infrared studies have shown us. There is a group of young stellar objects, much more numerous than the bright trapezium stars below the visible nebula. Some are protostars that still have thick rings around them, and others are brown dwarfs, which are objects below the stars that are too small to fuse. Because JWST was so accurate, scientists were able to measure the weak emissions from the tiniest of these things. This helped them figure out where the line between a planet and a star is. Based on what they discovered, the Orion Nebula may be one of the best places in the galaxy to find low-mass stars and brown dwarfs to form. Infrared images also revealed something unexpected: ripples in the surrounding gas that seem to change over time. By comparing Webb's data with decades of older infrared observations, scientists noticed that some filaments shift and brighten over mere years. These light echoes occur when radiation from a flare or shock front illuminates different parts of the cloud at different times. JWST's first Orion Deep Field. The James Webb Space Telescope, JWST, shocked even experienced scientists with its first deep field picture of the Orion Nebula. They thought it would be clearer, with maybe a few secret stars and better color contrast. They were surprised to find a whole new world, full of structure, motion, and complexity that changed everything they thought they knew about one of the most familiar parts of the sky. The infrared instruments on the telescope peeled back the nebula's glowing veil to reveal a stunning view of thousands of stars in all stages of their lives, from protostars that are just starting to form to giants that are fully grown and blazing through the gas around them. People saw Orion for the first time not as a picture of light and color, but as a live environment where things are made and broken down. JWST's Orion Deep Field combined data from its NIRCam and MIRI instruments, each capturing different wavelengths of infrared light. NIRCam traced the youngest, hottest stars, while MIRI revealed the faint heat signatures of hidden protostars buried in dust. The final image, a mosaic spanning nearly a full light-year of space, contained more detail than any previous observation of the nebula. Where earlier telescopes had shown smooth clouds, JWST resolved webs of filaments only a few astronomical units thick. Each filament was lined with beads of light, tiny newborn stars heating their surroundings, marking the locations of hundreds of miniature stellar nurseries. One of JWST's most remarkable discoveries in this image was the sheer abundance of previously unseen stars and outflows. Astronomers identified hundreds of new sources, many still in their earlier stages, radiating faintly through cocoons of gas. Some of these young stars emit narrow bipolar jets, visible as streaks of glowing plasma cutting across the image. These are the signatures of stellar birth, material being ejected at supersonic speeds from stars that are still gathering mass. In several places, JWST even captured these jets colliding with nearby clouds, creating ripples and shock fronts that spread like waves across the nebula. For the first time, scientists could trace these interactions across multiple scales, from tiny, individual systems to massive, multi-star networks spanning entire light years. The telescope also showed amazing changes in color and brightness, each of which was caused by a different chemical fingerprint. Areas of charged gas close to the trapezium cluster were marked by hydrogen that lit up red. Carbon monoxide showed up as orange bands that followed the paths of cooler molecular clouds. Polycyclic aromatic hydrocarbons, which are complex organic molecules, sparkled in blue and green on the surfaces of the dusty threads. These colors made something like a spectrum map of Orion's energy flow. It was the clearest picture yet of how ultraviolet radiation from very large stars shapes gas around them into waves, ridges, and arcs of light. The most fascinating component of the JWST deep field may have come from a place near the BNKL outflow, where the effects of an explosion that happened hundreds of years ago are still being felt today. The picture showed hundreds of bright bullets of gas, which were groups of gas thrown out by that ancient event and were still moving at over 100 kilometers per second. Some of these bright lines were as big as the solar system itself. They showed where hot iron and silicon are colliding with material in the environment. Astronomers were able to figure out the speeds, directions, and temperatures of these structures by looking at them in infrared light. This allowed them to recreate the blast that happened 500 years ago. It was like seeing a disaster from a long time ago that was frozen in space and still making noise. Another breakthrough came from the study of brown dwarfs, the elusive failed stars, too small to sustain fusion. JWST's sensitivity allowed scientists to detect dozens of these faint objects scattered throughout the nebula. Some appear to exist in pairs, orbiting one another like binary systems. Others drift alone, cooling slowly in the surrounding darkness. This discovery provided new clues about how substellar objects form, whether they're born like stars through gravitational collapse or ejected from larger systems during early chaos. The answer, based on JWST's findings, may be both. Orion seems to produce brown dwarfs in every possible way, proving that even failure is common in the story of creation. The telescope's infrared view also revealed hidden structures within the trapezium cluster itself. What had once appeared as a simple group of 4 stars turned out to be a gravitationally tangled web of multiple systems, each surrounded by smaller companions and disks. JWST's image showed overlapping outflows, intersecting shock fronts, and faint arcs of gas forming spirals around the most massive stars. These features suggest that close encounters between newborn suns are not rare events, but a natural consequence of dense star formation. The cluster, once seen as stable, now looked like a cosmic pinball machine, with stars bouncing and scattering under each other's gravitational pull. For the scientific community, the Orion Deep Field marked a turning point. The level of structural detail forced researchers to rethink long-standing models of how massive stars influence their surroundings. The nebula's filaments turned out to be more organized than expected, following paths that hint at strong magnetic alignment. At the same time, evidence of rapid small-scale motion revealed that the region is far more dynamic, with gas and dust shifting on timescales of mere decades. These dual characteristics, order and chaos, define Orion's new identity as revealed by JWST, not a static cloud, but a breathing organism of cosmic proportions. Stellar cannibalism. Deep in the densest parts of the Orion Nebula, stars aren't born quietly, they're born into chaos, with so many of them close to each other that gravity sometimes pushes them to crash into each other, killing them. In this world of stellar cannibalism, young suns don't just live together, they crash into each other, join and tear each other apart. New views from the James Webb Space Telescope show proof of these terrible interactions. Huge protostars that have eaten their partners, thrown others away, and left behind lines of hot debris that glow through the dust. Astronomers have thought for a long time that Orion's chaotic heart might hide this kind of violence. This is the first time they can see it happen. In a typical star-forming region, young stars form at safe distances from one another. But in Orion's BNKL region, The density is extreme. Thousands of newborn stars occupy a space barely a few light-years across. At that proximity, gravity becomes unpredictable. Stars tug at one another like dancers in a crowded ballroom, their orbits twisting, tightening, and sometimes crossing. When two protostars come too close, tidal forces can rip off material from one and feed it to the other. If they collide outright, they merge into a single, more massive star, releasing tremendous energy. Astronomers have identified such a recent event in Orion, a stellar merger that likely produced the BNKL explosion roughly 500 years ago, one of the most energetic outbursts in our galactic neighborhood. JWST's high-resolution infrared imaging has brought this ancient disaster into focus. It shows streams of hot gas radiating outward from a compact region, moving at hundreds of kilometers per second. At the center lies a knot of emission too bright and hot to be explained by ordinary star formation. The spectral signature reveals extreme heat, tens of thousands of kelvins, consistent with shock-heated material expelled during a violent stellar collision. The outflow is surrounded by irregular filaments and arcs, evidence that nearby stars were flung away by the gravitational recoil. Astronomers now believe this was not a single event, but a chain reaction. Multiple protostars scattering after a close gravitational encounter, their orbits destabilized and their surrounding disks shredded. These events are rare in most parts of the galaxy, but in Orion they may be almost routine. The nebula's high density and youth make it an ideal breeding ground for interactions. In the first few 100,000 years of a star's life, it's still surrounded by an accretion disk and embedded in thick gas. When two such objects approach, their disks collide first, generating drag and magnetic coupling that pull the stars together. The final merger releases gravitational energy equivalent to millions of nuclear bombs per second, enough to heat the surrounding gas and trigger shockwaves that ripple for light years. This process, often described as a stellar kiss, can create a new, hotter star, but it also destroys any planets or disks nearby, sterilizing the entire region. Some of the brightest infrared sources in Orion may be merger remnants, bloated protostars still glowing from the heat of their collision. JWST has observed objects whose luminosity exceeds what their mass should allow, suggesting that they recently merged and have not yet stabilized. These swollen stars will eventually shrink and settle, but for now, they radiate prodigiously, pouring ultraviolet light into the nebula and shaping its structure. In a sense, stellar cannibalism fuels Orion's beauty. The radiant energy that illuminates the gas is partly the afterglow of destruction. The gravitational chaos that leads to these mergers also explains the mysterious runaway stars ejected from the nebula. Observations have found several massive stars moving away from Orion at unusually high speeds, including the Becklin-Neugebauer object and radio source I. Their trajectories trace back to the same core where the 500-year-old explosion occurred. Models suggest they were once part of a compact multiple-star system that broke apart during a violent encounter. When two stars collided, the rest were flung outward by the sudden shift in gravitational energy. These runaways now travel through interstellar space like exiled suns, carrying with them the evidence of their chaotic birth. What makes stellar cannibalism so important to astrophysics is its lasting impact. Mergers can alter the stellar population of a region, creating abnormally massive stars that skew age and luminosity measurements. They can also seed turbulence by injecting energy into the surrounding gas, influencing where and when new stars form. In Orion, the after-effects of these events can be traced in the motion of nearby clouds and the expansion of cavities carved into the molecular gas. In short, every collision reshapes the nebula, leaving scars that will persist for millions of years. Long-held ideas about how stars grow are also called into question by the event. Most models of stars think that they get their mass mostly from slowly adding matter to their disks. In places like Orion, on the other hand, mergers may be a big part of how stars gain mass, especially for the biggest O-type stars. This means that the galaxy's biggest stars might not form by slowly eating smaller stars, but by crashing into each other and eating them until they hit a certain size. Such merger products may be found in the trapezium cluster itself. Their extreme shine hides a past of destruction. Rogue stars ejected from Orion. It's not always peaceful where a star is born in the Orion Nebula. Some are thrown into the void, thrown from their star homes at speeds so fast they can beat whole groups. These are stars that have gotten away from their parents, also known as rogue stars. Orion has a lot of them. These objects are the result of gravity chaos, which happens when a lot of young stars are crowded together and crash into each other or shoot out violently. Each star that is getting away is basically a messenger, bringing the scars of Orion's violence from one part of the sky to another. The story begins in the nebula's trapezium cluster, where thousands of young stars share a volume only a few light-years across. In this crowded environment, gravity constantly shifts the balance. Binary and triple systems form and dissolve. Protostars exchange companions like celestial pinballs. When two massive stars pass close enough, their gravitational pull can act like a slingshot. If one star in the pair happens to merge or lose mass during the encounter, the sudden imbalance can send one or more stars hurtling outward at astonishing speeds, sometimes exceeding 100 kilometers per second. These ejected suns are launched on trajectories that take them far beyond the nebula's glowing borders. Astronomers have been tracking several such fugitives for decades, using both radio and infrared telescopes. The most famous of them is the Böcklin-Neugebauer BN object, discovered in the 1960s as a bright infrared source moving rapidly away from Orion's core. BN is roughly 8 times the mass of the Sun and races through space at about 30 kilometers per second. Tracing its path backward, scientists found that it likely originated near the same region as Radio Source 1, another massive young star now moving in the opposite direction. Both appear to have been ejected by a violent three-body interaction roughly 500 years ago, the same event that caused the BNKL explosion. JWST and radio interferometers like ALMA have confirmed this connection by mapping the surrounding gas. The trails of molecular emission line up perfectly with the direction of these fleeing stars. It's as if the nebula still bears the scars of their departure, shock fronts, cavities, and elongated filaments all pointing away from the explosion's center. Simulations show that when massive protostars interact in such tight systems, one often ends up consuming or merging with another while ejecting the rest. The result is a chain reaction. One brightening star, one cataclysmic explosion, and a few high-speed exiles shot out into the galaxy. These runaway stars don't just leave silently, they carry violence with them. As they plow through the interstellar medium, their stellar winds compress and heat the gas ahead, forming bow shocks that glow faintly in infrared light. Space telescopes have captured several such arcs surrounding Orion's escapees, curved comet-like waves of material marking their passage. Each bow shock acts like a cosmic fingerprint, allowing astronomers to trace both the speed and direction of the fleeing star. Some of these waves stretch for light years, glowing as the rogue stars slice through interstellar gas like boats cutting across water. Not all runaways are massive giants. JWST has also detected smaller, sun-like stars and even brown dwarfs on trajectories that suggest ejection from Orion's core. These smaller objects likely formed as part of multi-star systems that became unstable during their early evolution. When one component gained mass too quickly or merged with another, the rest were thrown out. In many cases, these low-mass runaways retain their protoplanetary disks, albeit partially stripped by the encounter. It's possible that some of these wandering stars carry the first seeds of future planetary systems, doomed to drift through space alone, far from the environment that created them. The ejection of stars plays a crucial role in the long-term evolution of the Orion Nebula. Each time a massive star is flung outward, it takes with it a significant amount of energy and angular momentum. Over time, this process helps the central cluster stabilize, reducing the likelihood of further collisions. But it also spreads heavy elements and turbulence into the surrounding interstellar medium, enriching nearby regions and influencing the next generation of star formation. In this way, the nebula's violence has ripple effects that extend for hundreds of light years. By measuring their proper motion and tracing their trajectories backward, astronomers can reconstruct the history of the events that expelled them. Each rogue star's path leads to a point in Orion's heart, a timestamp marking where and when the explosion or encounter occurred. When multiple paths converge, they reveal the epicenter of a long-ago disaster. The BNKL region, with its trio of ejected stars, is now recognized as one of the most dramatic examples of this kind of stellar dynamical breakup ever recorded. Even after they escape, these stars remain connected to Orion in another way. Their radiation continues to shape the surrounding interstellar space, creating faint ionization trails that extend far beyond the visible nebula. In a sense, they drag pieces of Orion's light with them, carrying its energy into the galactic disk. Magnetic fields in the nebula. It looks like a mess when you first look at the Orion Nebula. There are clouds of gas in it, and radiation and gravity are making them bend, break, and crash into each other. But there is a hidden order underneath all that chaos, like a web that runs through all the dust and light that you can't see. That web is made up of magnetic fields. The nebula stays together even when strong winds want to break it apart. They are strong, secret forces that control the flow of gas and decide when stars are born. Orion would either break up into many small pieces or spread out into nothing without these fields. You can add them to it to make it even cooler, a machine that makes things and runs itself. Magnetic fields in space don't behave like the ones we experience on Earth. They're faint, measured in microgauss, yet they influence vast amounts of matter across light years. In Orion, these fields weave through the dense molecular clouds like invisible threads, aligning dust grains and shaping the direction of gas flows. When astronomers use instruments that detect polarized light, such as those aboard the Planck satellite and ground-based telescopes like JCMT and SOFIA, they can actually map these fields. The results are stunning: long, parallel filaments of polarization tracing elegant curves across the nebula, wrapping around its dense cores and extending outward into the surrounding interstellar medium. It's as if Orion's glowing clouds are draped over an invisible magnetic skeleton. The strength of these fields varies across the nebula. In the outer regions, where gas is thin and radiation dominates, the fields are relatively weak and diffuse. But deeper within, in the dense filaments of the OMC1 core, the magnetic field grows stronger, reaching levels that can counteract gravity itself. Measurements suggest that in some areas, the magnetic pressure is roughly equal to the gas pressure, a condition known as equipartition. This balance prevents the cloud from collapsing too rapidly under its own weight, moderating the rate of star formation. In essence, magnetism acts as a brake, slowing down gravity's relentless pull and giving stars time to form in stages rather than all at once. Magnetic fields also influence the shapes we see in Orion. Many of the nebula's filaments, those long, luminous strands of gas, follow the orientation of the magnetic lines. These filaments channel matter toward the dense clumps where stars are born, acting like interstellar highways. When stellar winds or shockwaves try to push gas in random directions, the magnetic fields resist, bending the flow and forcing it to move along set paths. This is why the Orion Nebula's structure appears so organized even in its turbulence. It's sculpted by an invisible hand that directs energy instead of allowing it to dissipate freely. The Hawk Plus instrument on SOFIA, which studies the polarized infrared light given off by warm dust grains, made one of the most exciting discoveries about Orion's magnetism. The data showed that the magnetic field lines around the trapezium cluster twist and curve in amazing ways, making structures that look like magnetic whirlpools. These arcs are probably caused by feedback between the huge O-type stars and the space around them. As the winds of these stars push outward, they pull magnetic lines with them, twisting them into complicated forms. In some places, the bending is so bad that it sends energy back into the gas, which can cause turbulence and maybe even the birth of new stars. So, Orion's magnetic field is not fixed. It's moving, changing shape all the time as the nebula changes. The role of magnetism becomes even clearer when we examine protostellar jets, the high-speed streams of gas ejected from young stars. These jets are guided by magnetic fields that spiral outward from the star's accretion disks. In Orion, hundreds of such jets have been observed, all perfectly collimated, meaning they stay narrow over vast distances. Without strong magnetic confinement, the jets would spread out and dissipate quickly. Instead, they remain focused, carrying angular momentum away from the forming stars. This process helps young stars stabilize and regulate their growth, preventing them from collapsing or spinning apart. In this way, Orion's magnetic fields serve as both architects and stabilizers, shaping stars from the moment they're born. Even the Orion bar, that bright dividing line between ionized and molecular gas, owes its razor-sharp edge partly to magnetism. Observations show that magnetic field lines there run parallel to the boundary, strengthening as radiation pressure compresses the gas. These aligned fields trap particles and control how heat and radiation spread across the transition zone. The result is the bar's striking definition, a magnetic curtain separating light from shadow. Sound in the void, shockwaves and turbulence. There is no such thing as silence in the Orion Nebula. We may think that space is empty, but the gas and dust in Orion's dense molecular clouds are thick enough that pressure waves can travel through them. These waves are like sound that travels through the space between the stars. Even though these waves move much more slowly than light, they are very powerful. They change the way the nebula changes over time, move its gas around, and even help start new generations of stars. Astronomers see Orion not as a still picture of the beginning of time, but as a live, vibrating structure that is echoing with the shockwaves of its own violence. We can see the ghost of motion below the surface in every wave of light we see. The main drivers of this turbulence are the massive O-type and B-type stars of the trapezium cluster. Their stellar winds, high-speed streams of charged particles, crash into the surrounding gas at hundreds of kilometers per second. When these winds collide with slower-moving or denser regions, they create shock fronts, regions where pressure, temperature, and density suddenly spike. These shocks compress gas into thin, bright filaments that glow in hydrogen and oxygen emission lines. In visible light, they appear as curved ridges or arcs, like the ripples around a stone dropped in water. Each one marks the boundary where the energy from massive stars meets the resistance of cold molecular gas. Unlike explosions on Earth, these cosmic shockwaves don't move through air. They travel through plasma, a mix of ionized gas and magnetic fields. When they pass, they heat the material to thousands of degrees, stripping electrons from atoms and causing the gas to glow. This is what gives Orion its shimmering, textured appearance. Overlapping shock fronts moving through gas of varying density, each creating a thin sheet of light. Some shocks expand outward from the trapezium cluster, while others are generated by newborn stars' outflows deep within the molecular cloud. The entire region is a web of colliding fronts, constantly shifting and colliding. Astronomers studying Orion with instruments like JWST, Hubble, and the Chandra X-ray Observatory have discovered that these shock waves don't just make the nebula beautiful, they regulate its entire life cycle. When a shock compresses gas beyond a certain threshold, gravity takes over, causing that region to collapse into a new protostar. But if the shock is too strong, it blows the gas apart instead, halting star formation. This delicate balance between triggering and destroying defines the nebula's evolution. In Orion, both effects are happening simultaneously. The same winds that sculpt its elegant forms also tear holes in them, ensuring that creation and chaos coexist at every scale. Some of the most dramatic shocks in Orion occur in the BNKL region, the site of a stellar explosion about 500 years ago. Radio and infrared observations reveal streams of gas, called molecular bullets, moving outward at speeds up to 150 kilometers per second. As these bullets plow into denser material, they generate bow shocks that light up in infrared and visible wavelengths. Each glowing arc is a snapshot of a high-energy collision that continues to send vibrations through the cloud. If we could translate these movements into sound, the Orion Nebula would hum and roar with frequencies far below human hearing, a deep, resonant chorus of creation. Turbulence plays a central role in this ongoing symphony. The nebula's interior is far from calm. It's a boiling ocean of motion. Gas swirls in eddies and vortices spanning light years, each driven by feedback from stars and magnetic forces. Measurements show that this turbulence follows a pattern known as supersonic flow, meaning the gas moves faster than the local speed of sound. When these turbulent flows intersect, they produce secondary shocks, further stirring the nebula. This constant agitation prevents the gas from collapsing too quickly under gravity, stretching out the star formation process over millions of years. In this sense, Orion's turbulence is both destructive and creative. It tears apart clouds even as it seeds the next generation of stars. Magnetic fields amplify this turbulence. As charged particles move through magnetic lines, they twist and stretch the fields, generating waves known as magnetosonic waves. These waves carry energy across the cloud, redistributing momentum and maintaining the nebula's internal pressure. Observations suggest that magnetosonic turbulence may be responsible for the intricate filamentary texture seen in Orion's images. Each thread of light represents a balance point between gravity, motion, and magnetic tension, a frozen sound wave captured in glowing gas. Some of Orion's structures have even shown changes in time, which suggests that shockwaves are moving through the area on timescales of only a few years. These shifts show up as small changes in form or brightness, mostly near the trapezium cluster's edges. This is a warning that the Orion Nebula is not still. It's alive and changes all the time, even in our own lifetimes. What we see through telescopes is a picture of a process that is still going on. It shows a cosmic storm that is always moving. Cosmic chemistry in action. The Orion Nebula is both a storm of energy and a lab. It's a huge chemistry workshop where atoms, dust, and radiation come together to make some of the most complicated reactions anyone has ever seen outside of our solar system. The universe is like a huge game of alchemy. It is making the molecules that will one day form planets, stars, and maybe even the building blocks for life. Astronomers and astrochemists see Orion as more than just a place where stars are born. They see it as a place where science comes to life. The nebula's gas may look simple, but it's anything but. More than 60 different molecular species have been identified within the Orion molecular cloud, making it one of the richest chemical environments known. The most abundant element is hydrogen, found both as atomic hydrogen, Hi, and molecular hydrogen, H2. But mixed within are carbon monoxide, ammonia, formaldehyde, methanol, sulfur dioxide, silicon monoxide, and a host of other compounds. These molecules aren't static. They're constantly forming, breaking apart, and recombining as radiation and shock waves ripple through the cloud. Every spark of ultraviolet light, every shock front, every turbulent swirl adds energy to drive new reactions. In the coldest parts of the Orion cloud, where temperatures dip below 30 kelvins, dust grains act as tiny chemical factories. Atoms and molecules stick to their icy surfaces, forming thin mantles of frozen material. On these microscopic laboratories, hydrogen atoms combine to form molecular hydrogen, the most basic and essential reaction in the universe. Oxygen and carbon assemble into water and carbon monoxide. Nitrogen bonds with hydrogen to form ammonia. Over time, as these icy layers build up, more complex molecules begin to appear: formaldehyde, H2CO, methanol, CH3OH, and other organics that can serve as precursors to sugars and amino acids. These are the same kinds of molecules found in comets and meteorites within our own solar system, suggesting that Orion's chemistry may mirror the early stages of our own origins. But in Orion, even chemistry is violent. The nebula's ultraviolet radiation, especially from the trapezium stars, bombards the gas with high-energy photons that break molecular bonds, a process known as photodissociation. This destruction, paradoxically, creates opportunities for new molecules to form. When a photon splits a molecule apart, it produces reactive fragments called radicals, which can recombine into new arrangements. The region known as the Orion bar is one of the best examples of this process in action. A razor-thin layer where ultraviolet light meets molecular gas, generating a chemical frontier between destruction and creation. Spectroscopic data from the James Webb Space Telescope show the bar glowing with emission from carbon, oxygen and hydrogen recombining, the literal glow of chemistry at work. When supersonic jets from young stars slam into dense gas, the resulting heat and pressure drive endothermic reactions that wouldn't occur in calmer conditions. In the BNKL outflow region, where a massive explosion occurred about 500 years ago, molecules like silicon monoxide and sulfur monoxide are found in extraordinarily high concentrations, evidence of violent shock chemistry. The collision of gas fronts can momentarily raise temperatures to thousands of kelvins, vaporizing ice mantles on dust grains and injecting new species into the surrounding gas. Once the shock cools, these liberated molecules combine in fresh ways, creating entirely new compounds. It's a cycle of destruction and renewal that turns Orion into a molecular forge. Infrared spectroscopy from JWST and ALMA has revealed even more exotic chemistry within these turbulent zones. Observations show spectral signatures of polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules with ring structures similar to soot. PAHs are thought to be precursors to even larger organic systems, potentially linking interstellar chemistry to prebiotic processes. These molecules fluoresce when excited by ultraviolet light, producing the characteristic teal-blue glow seen in many images of Orion. Their presence proves that carbon chemistry can thrive even under intense radiation, an encouraging clue for scientists studying how organic material spreads through the galaxy. The molecular diversity doesn't end there. Traces of deuterated molecules, compounds containing the heavy isotope of hydrogen, have also been found in Orion's cold regions. These molecules form under unique conditions of low temperature and density, and their abundance gives astronomers clues about the nebula's thermal history. The ratio of deuterium to hydrogen, for instance, can reveal how long certain pockets of gas have remained cold, a molecular clock ticking quietly inside the storm. Even water, the molecule most essential to life as we know it, plays a starring role here. Water vapor has been detected in multiple zones of the Orion cloud, from the warm outflows of protostars to the cooler outer filaments. Some of this water likely formed on dust grains and was released into the gas phase by shock heating. These discoveries are more than symbolic. They show that the raw materials for planetary oceans already exist long before planets themselves do. Orion, in this sense, is not just forming stars, it's preparing the ingredients for worlds. It might seem impossible for complex molecules to survive the harsh conditions where all of this chemistry takes place. But Orion shows that's not true. It shows that the building blocks of life can appear in the midst of radiation, shockwaves, and chaos in space. Scientists' ideas about habitability have changed since they learned this. If complex chemicals can form here, in a place in the galaxy where stars are least likely to form, then they can form almost anywhere. Chemically, it looks like the world wants to do a lot. Lightning in space, plasma discharges, and ion fronts. If we could get close enough to the Orion Nebula to see its real power, we would see more than just glowing clouds and soft colors. We would see flashes. Electricity flickers through the gas. Charged particles rush along magnetic paths that can't be seen, and huge arcs of plasma discharges weave between areas of different energies. This is the side of Orion that we can't see. It's a world of ion fronts and plasma lightning, and electromagnetic forces are in a battle with gravity and radiation to shape the nebula's structure. In space, lightning doesn't behave the way it does on Earth. There are no clouds heavy with water droplets or simple thunderbolts striking the ground. Instead, The lightning of Orion takes the form of electrical discharges through plasma, the ionized gas that fills much of the nebula. Plasma, often called the fourth state of matter, conducts electricity freely because its atoms are stripped of electrons. This makes it extraordinarily sensitive to electromagnetic fields. When local regions of plasma become unstable, due to turbulence, radiation pressure, or magnetic reconnection, they can unleash bursts of energy along filamentary currents, illuminating the surrounding gas in brief flashes of ultraviolet and X-ray light. Astronomers have long recognized Orion as one of the most electrically active regions in the nearby galaxy. Observations from the Chandra X-ray Observatory and Sophia's Hawk Plus instrument show strong signs of magnetically driven heating throughout the nebula. In particular, the region near the Orion bar, where hot ionized gas meets cold molecular gas, acts like a massive electrical boundary. The difference in charge and temperature creates what scientists call an ionization front, a transition zone where electrons recombine with ions, releasing light and heat in the process. In essence, these fronts function like cosmic lightning sheets, vast, slow-motion discharges that trace the flow of energy from the trapezium cluster into the nebula. Magnetic reconnection is one of the most important parts of this process. This is what happens when magnetic field lines break and rejoin, releasing huge amounts of energy. It works the same way as solar flares on Earth, but on a much bigger scale in Orion. The lines get twisted and stretched until they break when the stellar winds from big O-type stars hit the nebula's magnetic fields. The energy that is released can heat gas to millions of degrees and make plasma bubbles that emit X-rays and grow through the cloud. In some cases, these events may even cause short bursts of radiation strong enough to ionize new areas of gas, shaping the bright edges of Orion. At smaller scales, electrical currents within the nebula manifest as narrow filaments, long, thread-like structures of glowing gas that trace the paths of charged particles. High-resolution images from JWST and Hubble reveal dozens of these filaments snaking through Orion's core, often converging near the trapezium cluster or along shock fronts. These are not static features. They flicker and shift over time as currents rise and dissipate. Some are likely the results of collisions between stellar winds, where streams of ionized particles flow together and momentarily generate enough voltage difference to spark a discharge. Though brief by cosmic standards, lasting perhaps minutes or hours, these events can release more energy than millions of lightning bolts on Earth combined. Scientists believe these discharges play a crucial role in the nebula's chemistry and structure. When high-energy electrons race through gas, they collide with atoms and molecules, exciting them to higher energy states. As the excited atoms return to normal, they emit photons, the light we see as Orion's glow. These collisions also break apart stable molecules, allowing new reactions to occur. In this way, plasma discharges act as both sculptors and chemists, driving ionization and stimulating molecular diversity across the nebula. The characteristic emerald and crimson hues in Orion's brightest regions are direct consequences of these energetic processes, particularly emission from doubly ionized oxygen and hydrogen alpha radiation. The Orion Nebula's electrical activity also extends into its shock fronts and Herbig-Haro objects. When supersonic jets from young stars strike ionized gas, they generate bow-shaped structures that glow from both thermal and electrical excitation. As magnetic fields are compressed and twisted in these zones, localized currents surge through the plasma, releasing bursts of heat and light. In some cases, observations show brief enhancements in brightness that fade within years, the celestial equivalent of a lightning storm's afterglow. These events reveal how intimately electricity, magnetism, and motion are intertwined in the nebula's evolution. The Orion Nebula cluster's population. In the Orion Nebula's bright mist, there is a crowded star city with a population so dense and varied that it works like a small version of our galaxy. The Orion Nebula Cluster, O1c, is a group of more than 2,000 stars that are held together by gravity in a space only a few light years across. The group looks like the bright heart of Orion's sword to the naked eye. Behind that familiar glow is a hive of movement, young stars spinning, crashing into each other, and engaging in ways that have changed not only the nebula's light, but also the futures of many possible planetary systems. The Orion Nebula cluster is astonishingly young. Most of its stars are less than 2 million years old, still in their cosmic infancy. Many are surrounded by protoplanetary disks, some still gathering material, others already sculpted by the fierce radiation of the trapezium's massive stars. The cluster represents nearly every stage of stellar evolution within its early phase. From cool, dim brown dwarfs, barely above the threshold of ignition, to brilliant O-type suns, blazing with enough energy to light up entire regions of space. This diversity makes the ONC one of the most important natural laboratories in astrophysics. At the cluster's center lies the famous trapezium, a small group of massive O and B stars, whose combined radiation dominates the nebula. These giants, particularly Theta 1 Orionis C, are the engines that power Orion's glow. They flood the region with ultraviolet light, ionizing the surrounding hydrogen and sculpting the iconic structures we see from Earth. But their dominance also makes the ONC a dangerous place to grow up. Their intense radiation strips material from nearby disks and evaporates gas around smaller stars, threatening to halt planet formation before it can begin. This is why astronomers refer to Orion as both a cradle and a crucible, a place where stars are born, but few are allowed to mature undisturbed. Surrounding the trapezium is a swarm of lower mass stars, K and M dwarfs that make up the bulk of the cluster's population. Many of these are variable stars, flickering as they accrete material or experience magnetic flares. Observations from NASA's Chandra X-ray Observatory show that these young suns are remarkably active. Their magnetic fields twist and reconnect constantly, unleashing flares 1,000 times stronger than the sun's most powerful storms. The nebula's X-ray glow is largely produced by this collective magnetic fury, a continuous fireworks display of newborn stellar activity. Each flare injects energy into the surrounding gas, stirring turbulence and contributing to the nebula's restless character. Even smaller members populate the ONC's outskirts, brown dwarfs, objects too small to ignite hydrogen fusion. Discovered in large numbers by infrared surveys, these failed stars bridge the gap between giant planets and true stars. Some are only a few times the mass of Jupiter, yet they radiate heat from the energy of their formation. JWST and ALMA have detected disks around several of these brown dwarfs, suggesting they too might host miniature planetary systems. These discoveries blur the line between planets and stars, showing that nature doesn't draw sharp boundaries. It produces a continuum of worlds across scales. What the cluster is made of also tells us about its history. At their heart, the stars are very close to each other, so close that they often bump into each other due to gravity. Some stars rotate in pairs or trios, while others have already been thrown out by close encounters and are now running away from the nebula. As you move farther away, the density drops, making a ring of younger stars that are still surrounded by the molecular cloud. This change from a dense, fully developed core to a scattered, still-forming edge suggests that the ONC is still putting itself together. It's likely to spread out over the next few million years as radiation and stellar winds blow away the leftover gas. What will be left is an open clump of young stars moving through space. Despite its crowding, the ONC is remarkably balanced. Gravity pulls its stars inward, but radiation and stellar winds push outward. Magnetic fields weave through the gas, distributing tension and maintaining structure. This equilibrium allows the cluster to sustain star formation, even while older members already shine brightly. It's a cosmic balancing act, a system both stable and dynamic, constantly shifting yet persisting long enough for thousands of stars to emerge. The variety of stellar ages and masses within the ONC provides astronomers with a unique opportunity to study how stars evolved together. By measuring luminosity, rotation, and chemical composition, scientists can trace the timeline of the nebula's birth. What they've found is that star formation in Orion didn't happen all at once. It came in waves. The oldest stars formed several million years ago, followed by younger generations, triggered by feedback from earlier ones. This cascading sequence, older stars igniting, shocking nearby gas, and birthing new stars, explains why the nebula remains so active today. It's not one event, but a continuous process spanning eons. Brown dwarfs and failed suns. In the Orion Nebula, not every new thing that comes out doesn't turn into a star. There are some that never hit the right amount of mass and pressure to start hydrogen fusion in their cores, which is what makes a star. Brown dwarfs, which are sometimes called failed suns, are these hard-to-find bodies. These things live in the area between planets and stars. They are too heavy to be worlds and too light to shine like their star cousins. For decades, they were just interesting ideas. But telescopes have found a lot of them in the thick center of Orion, quietly shining in infrared light. They are a group of almost invisible suns that mark the beginning of time. To understand brown dwarfs, we need to recall how stars are born. Every star begins as a collapsing pocket of gas within a molecular cloud. As gravity pulls the gas inward, it heats up, and the pressure at the core rises. If the object gathers enough mass, roughly 0.08 solar masses, or about 80 times the mass of Jupiter, the temperature climbs above 10 million kelvins, and hydrogen fusion ignites. The star is born, but if the mass stays below that threshold, gravity alone isn't enough to trigger fusion. The collapse eventually stops, halted by quantum pressure inside the dense core. The result is a brown dwarf, an object still warm from its formation, but fated to cool and fade over billions of years. The Orion Nebula is one of the best places in the galaxy to study these mysterious bodies because it's young and nearby. Using the Hubble Space Telescope, Spitzer, and now the James Webb Space Telescope, astronomers have detected hundreds of brown dwarfs scattered across the nebula. Most are found in the outer regions of the Orion Nebula cluster, where the density of gas and radiation is lower, a quieter environment that allows smaller objects to survive. They range in mass from about 70 Jupiter masses at the high end down to barely 10 at the low end, overlapping with the most massive exoplanets. Some even appear to drift freely through the nebula, unbound to any parent star, the so-called rogue planets of interstellar space. Infrared observations reveal that many of these brown dwarfs still retain protoplanetary disks, just like full-fledged stars. These disks are smaller and less massive, but they contain dust and gas that could, in theory, form moons or miniature planets. ALMA and JWST have even identified faint rings and gaps around a few of these objects, signs of nascent planet formation. It's a humbling discovery. Even failed stars can spawn their own systems, complete with worlds orbiting a dim, cooling sun. This blurs the very definition of what it means to be a solar system. The light emitted by brown dwarfs isn't steady starlight. It's mostly heat, infrared radiation from the slow cooling of their interiors. Early in their lives, they can reach temperatures of several thousand kelvins, glowing with a dull orange-red hue. Over millions of years, they fade into the background, becoming nearly invisible. But during their youth, they shine just brightly enough for sensitive telescopes to detect their signatures. By comparing these infrared fingerprints, astronomers can estimate their age, temperature, and chemical makeup. The brown dwarfs in Orion show a remarkable spread, some hot and bright, others already cooling, suggesting they formed at slightly different times, perhaps over multiple generations of star formation within the nebula. How do brown dwarfs form in the first place? That question remains one of Orion's great mysteries. Some may form like stars, through the direct collapse of small gas fragments that never gather enough material. Others might begin as ordinary protostars, but are ejected from their birthplaces before they can grow, victims of gravitational chaos in the crowded trapezium cluster. A third possibility is disk fragmentation. In the outer regions of a massive protoplanetary disk, clumps of gas may condense and separate, forming a brown dwarf rather than a planet. Orion, with its high density and violent interactions, likely produces all three types. Each brown dwarf, then, is a fossil record of a different pathway to partial stardom. The huge number of Orion's brown dwarfs is one of the most captivating aspects about them. Surveys show that one brown dwarf is made for every 2 or 3 stars that are formed in the nebula. This number is a lot higher than what early models said it would be. This means that low-mass creation is not a mistake, but a natural result of how molecular clouds break apart. It looks like the universe would rather make small, dim things than big, bright ones. Most of these won't be seen as they wander the sky as billions of weak embers floating between the stars. They are remnants of old nurseries like Orion. X-ray fury. In the calm glow of the Orion Nebula, there is a secret storm of energy that we can't see, an ocean of X-rays that flashes and flares with great power. These high-energy emissions show a side of Orion that optical telescopes could never see, a world ruled not by soft starlight, but by magnetic chaos, plasma storms and stars that flare out with enough power to burn whole planetary disks. Looking at Orion through X-rays is like taking off the veil of its beauty and seeing how stars are born, chaotic, powerful, and incredibly fierce. The first hints of Orion's X-ray activity came in the 1970s with early space observatories, but it wasn't until the launch of NASA's Chandra X-ray Observatory that the full picture emerged. When Chandra turned its sharp X-ray eyes toward the Orion Nebula, the results were jaw-dropping. What looked like a tranquil cloud in visible light turned into a glittering field of more than 1,600 X-ray sources, each corresponding to a young, energetic star. The nebula's soft glow was replaced by a seething cauldron of flares and bursts, with radiation levels far beyond anything produced by our Sun. For astronomers, it was the equivalent of looking into the beating electric heart of a stellar nursery. So where does all this energy come from? The answer lies in the powerful magnetic fields generated by young stars. During their early years, stars rotate rapidly, often once every few hours, and their interiors churn with convection, generating intense magnetic activity. These magnetic fields twist, snap, and reconnect in explosive events known as magnetic reconnection, the same process that drives solar flares on the Sun, but on a vastly greater scale. Each time a reconnection occurs, it releases enormous amounts of energy, heating nearby plasma to tens of millions of degrees. The result is a sudden X-ray flare, a cosmic lightning storm radiating across the nebula. In the Orion Nebula cluster, such flares are constant. Some stars erupt several times a day, each outburst lasting hours and releasing as much energy as the Sun emits in a week. The most extreme events, known as superflares, can briefly outshine the star's normal light by a factor of hundreds. These eruptions are powerful enough to strip nearby planets of atmospheres or sterilize them entirely. For young solar systems, X-rays are both a hazard and a shaping force. They heat and ionize gas in protoplanetary disks, influencing how planets form, migrate, and evolve. In a very real sense, X-rays are part of the sculpting toolkit of creation. Chandra's long-term monitoring of Orion revealed that the nebula's X-ray emissions vary dramatically depending on the type and age of the star. Massive O and B-type stars, such as those in the trapezium cluster, produce steady streams of X-rays through their powerful stellar winds. As these winds collide with one another and with the surrounding gas, they generate shocks that emit continuous high-energy radiation. Smaller, sun-like stars, however, produce X-rays in bursts, driven by magnetic storms on their surfaces. Together, these two mechanisms fill the entire nebula with overlapping waves of energy, a diffuse X-ray fog that extends for dozens of light-years. The trapezium cluster itself is a powerhouse. The brightest of its members, Theta 1 Orionis C, emits millions of times more X-ray energy than the Sun. This single star's magnetic field interacts with its supersonic wind, creating shock zones where plasma is heated to extreme temperatures. Observations suggest that the star's magnetic poles channel its wind into streams that collide near the equator, producing pulses of X-ray emission that fluctuate rhythmically. In effect, the trapezium's giants are not just luminous, invisible light. They're blazing beacons of high-energy radiation, constantly bombarding the surrounding gas with invisible fire. These X-rays don't just escape into space, they have profound effects on their environment. When they strike the surrounding molecular gas, they ionize atoms and drive chemical reactions that wouldn't otherwise occur. In the dense OMC-1 core, X-rays penetrate deeply, heating pockets of gas and changing how molecules form. This process, known as X-ray dissociation, creates unique zones rich in exotic ions and radicals, contributing to Orion's complex chemistry. It also influences how magnetic fields behave. Ionized gas couples more strongly to magnetic lines, altering the balance between gravity and pressure that determines how clouds collapse into stars. Chandra's studies also led to the amazing discovery of X-rays coming from protostars that were still buried deep inside their dusty cocoons. These young suns make strong magnetic flares that punch through the dust around them and light up the cloud from within, even before they reach full stellar ignition. In other words, magnetic activity and the X-ray noise that comes with it start before a star is born, not after. These early flares may have a big part in controlling accretion, which keeps protostars from getting too heavy too fast. The life and death of massive stars. Most of the light sources in the Orion Nebula are doomed to fail. The trapezium cluster is made up of big O and B-type stars that die quickly and furiously, using up their nuclear fuel at unimaginable speeds. They're what make Orion shine, the builders of its light and the artists of its structure. But each one also holds the timer for destruction. Seeing these stars is like seeing a cosmic paradox. The forces that keep the nebula alive are also getting it ready to die. Massive stars form quickly, collapsing from the densest pockets of gas in the nebula's molecular cloud. While small stars like the Sun take tens of millions of years to ignite, an O-type star can reach full fusion in less than 100,000. Once active, their cores burn ferociously, fusing hydrogen into helium and releasing energy millions of times greater than that of a typical star. Their temperatures soar to over 30,000 kelvins. Their ultraviolet radiation ionizes the gas around them, and their powerful stellar winds sweep the nebula clean, blowing cavities into the surrounding dust. They are short-lived but spectacular, the fireworks of the cosmos. The most massive of Orion's stars, Theta 1 Orionis C, embodies this extreme lifestyle. At roughly 40 solar masses, it will spend only a few million years on the main sequence before exhausting its hydrogen. Already it dominates the nebula's radiation field, shaping everything within dozens of light years. The gas filaments, glowing arcs, and hollow cavities that make Orion so photogenic all trace back to its energy output. But such intensity comes at a cost. As it burns through its fuel, the core grows unstable. Fusion shifts from hydrogen to helium, then to heavier elements like carbon and oxygen, building layers like an onion. Each new stage burns faster than the last, hastening the star's inevitable collapse. The life cycles of these massive stars are intertwined with the nebula's fate. Their stellar winds inject enormous amounts of energy into the surrounding gas, creating shockwaves that compress nearby clouds and trigger new bursts of star formation. This feedback loop ensures that while one generation of stars blazes and dies, another begins to form in its wake. But the process is inherently destructive. Over time, the radiation and winds from the trapezium's giants will erode the remaining molecular gas, blowing it out into space and ending Orion's star-forming era. The nebula's current brilliance is, in fact, its swan song, the final flare of activity before it fades into a naked cluster of stars. Eventually, the most massive members will meet their explosive end as supernova. When the core runs out of fuel, it can no longer support the crushing weight of gravity. The outer layers collapse inward, rebound off the dense core, and blast outward in a titanic explosion. In a fraction of a second, the star releases more energy than the Sun will produce in its entire 10 billion-year lifetime. The shockwave races through the surrounding gas, compressing, heating, and reshaping everything it touches. In Orion, such explosions will someday send shock fronts across light years, tearing through the nebula's remaining clouds and triggering the birth of new stars in distant regions. Supernovae are more than acts of destruction, they are acts of creation. Within their dying cores, elements heavier than iron are forged through rapid nuclear reactions. Gold, silver, iodine, uranium, all the complex atoms that make up planets and life are born in these brief moments of cosmic violence. When the shockwave spreads, it scatters this material into the interstellar medium, seeding future generations of stars with the building blocks of complexity. Every atom of calcium in our bones and iron in our blood once came from such an explosion. Orion's future supernovae will someday enrich the galaxy in the same way, continuing the chain of creation through death. The aftermath of a supernova depends on the star's mass. Those at the lower end of the massive range may leave behind a neutron star, a dense sphere only a few kilometers wide but containing more mass than the Sun. The more extreme giants collapse completely, forming black holes that vanish from sight but remain gravitationally bound to the cluster. Some of these remnants may linger quietly, others might merge or accrete material, releasing bursts of X-rays that will once again light up the region long after the visible nebula has faded. In either case, Orion's legacy will include not just the stars we see now, but the compact relics of those that lived too brightly to last. Supernova seeds, the past explosion that triggered Orion. A long time ago, before the Orion Nebula turned into the bright sight it is now, this part of space was lit up by a different kind of fire, the death of a huge star. They now think that a supernova explosion millions of years ago may have been the event that caused Orion to form. The blast from that disaster tore through the interstellar medium around the stars, pressing down on huge clouds of hydrogen and dust, and starting a chain reaction that is still going on today. It's possible that Orion's birth began with the death of another star. Evidence for this ancient explosion comes from the large, faint arcs of gas and dust surrounding the nebula, most notably the immense structure known as Barnard's Loop. Stretching across the night sky in a sweeping red arc nearly 300 light-years wide, Barnard's Loop forms a near-perfect circle centered around the Orion constellation. Astronomers have long suspected that this loop is the remnant of a supernova, its glowing hydrogen gas energized by the radiation from nearby stars. Recent studies using radio and X-ray data have confirmed that the loop is indeed an expanding shell of gas, moving outward at about 100 kilometers per second, the telltale speed of a long-cooled supernova shockwave. Inside that vast bubble lies the entire Orion molecular cloud complex, including the Orion Nebula, the Horsehead Nebula, and dozens of smaller star-forming regions. This isn't a coincidence. The compression caused by the supernova's blast would have squeezed pockets of gas within the cloud, triggering the gravitational collapse that formed the first protostars. Over time, those new stars created their own winds and radiation, igniting additional waves of star formation. A domino effect that continues to ripple outward through the complex even today. In this sense, the Orion Nebula isn't just an isolated structure. It's one chapter in a much larger cosmic chain reaction set off by a long-dead star. The idea of supernova-triggered star formation is well established in astrophysics, but Orion offers one of the clearest examples. Observations from the Rosat and XMMM Newton X-ray observatories show hot plasma filling the cavity of Barnard's Loop, evidence of an old explosion's lingering energy. The surrounding clouds, including Orion A and Orion B, show compressed edges facing the loop's center, consistent with being pushed by an expanding shock front. Even the age gradient of stars across the Orion complex supports the theory. The oldest stars lie closest to the presumed explosion site, while younger clusters, like the Orion Nebula cluster, are found farther out, along the advancing front. This sequence tells a clear story. A wave of creation moving steadily through space and time, leaving a trail of newborn stars in its wake. Some astronomers have gone further, proposing that more than one supernova contributed to Orion's formation. The region known as the Eridanus superbubble, a vast cavity filled with hot gas, appears to have been carved out by multiple supernovae over the past 10 million years. Each explosion added energy, expanding the bubble and compressing its edges, where new stars, including those in the Orion Nebula, eventually ignited. This cyclical process of destruction and creation may be the key to understanding why Orion is such an active stellar nursery. Every generation of stars sows the seeds for the next through its own violent demise. If this interpretation is correct, then the Orion Nebula itself is living on borrowed time, caught in the brief, brilliant phase between collapse and dispersal. The very forces that birthed it will, in turn, destroy it, just as its predecessors did. Already, massive stars within the nebula are sending out winds strong enough to carve cavities in the molecular cloud. In a few million years, those same stars will explode as supernovae, driving new shockwaves through the region. Their remnants will merge with Barnard's loop, expanding the superbubble and potentially triggering yet another cycle of star formation farther away. The Orion we see today is therefore not a permanent fixture, but a transient flare in an ongoing galactic rhythm, a heartbeat in the Milky Way's vast living body. Clues to this earlier supernova also linger in the chemical fingerprints of Orion's gas. Spectroscopic studies have detected enhanced levels of heavy elements, oxygen, silicon, and sulfur, which are typical products of supernova nucleosynthesis. These elements enrich the nebula's dust, providing the raw material for planets and complex chemistry. The isotopic ratios of oxygen and neon in Orion's gas match those expected from a supernova remnant roughly 6 million years old, strengthening the case that the nebula's existence owes itself to an ancient explosion. Even the faint X-ray glow that pervades the region could be residual heat from the expanding supernova shell that first set the process in motion. It's a powerful reminder that in the world, making things and destroying them are not opposites, but rather parts in the same play. The death of one star can make thousands more come into being. Millions of years ago, the explosion that went through Orion's gas didn't end anything. It began something. The bright clouds we see now, the stars that are being born, and the chemically rich space that will one day support planets are all the effects of a supernova that happened a long time ago. The future supernova candidate. There are a lot of bright young stars in the Orion Nebula, but one of them has a deadly secret. The nebula's glow comes from radiation that shines through our telescopes, but its brightness is also a warning. This star, Theta 1 Orionis C, is the biggest and strongest in the trapezium cluster. It is not only Orion's lighthouse, but it will also destroy it in the future. Astronomers now think that this very large O-type giant, which is about 40 times the mass of the Sun, is not going to last much longer. It will explode in a supernova in a few million years, which is a blink on the cosmic clock. The supernova will change the shape of the nebula and mark the end of Orion's luminous age, Theta. 1. Orionis C is the undisputed ruler of Orion's sky. Its surface temperature exceeds 40,000 kelvins, and it emits more ultraviolet radiation in a single day than the Sun does in an entire lifetime. This radiation is what gives the nebula its characteristic glow, stripping electrons from surrounding hydrogen atoms and making them recombine in waves of visible light. Without this single star, the Orion Nebula as we see it would vanish from view. But that same energy output is also a sign of instability. Massive stars like Theta C live fast and die young. Their cores burn through hydrogen in a few million years, and the transition to helium fusion marks the beginning of the end. Astronomers studying the spectral lines of Theta C have detected signs of internal turmoil. Its surface pulses with powerful stellar winds moving at thousands of kilometers per second, carrying away material equivalent to the mass of the Earth every few days. These outflows are not steady. They fluctuate, suggesting the star's outer layers are unstable. Even more intriguing, the star possesses an intense magnetic field, roughly 10,000 times stronger than Earth's. This field traps and channels its wind into twisted loops of plasma that extend far into space. As these magnetic structures collapse and reconnect, they release bursts of energy, miniature magnetic storms that can heat the surrounding gas and alter the flow of matter across the nebula. Such instability is a hallmark of a star nearing the end of its stable life. As Theta C continues to fuse heavier elements, its core contracts while its outer layers expand and fluctuate. Eventually, it will exhaust the fuel that maintains balance between radiation pressure and gravity. When that happens, the core will collapse in a fraction of a second, igniting a supernova that will rival the brightness of an entire galaxy for weeks. The shockwave will race outward at thousands of kilometers per second, tearing apart the remaining gas and dust of the Orion Nebula, and leaving behind either a neutron star or a black hole. The Orion we know will be gone, replaced by a glowing remnant expanding into the void. Such an event would have huge effects that would be felt all the way to the edge of the galaxy. It would destroy the nebula's fine strands and bright arcs, which were all shaped by Theta C's light. As the blast squished nearby gas clouds, it could start new rounds of star formation on the edges of Orion, similar to the supernova that probably created it millions of years ago. In this way, the circle of birth and death would keep going, with the death of Theta C planting the seeds for new stars to come. Carbon, oxygen, silicon, and iron are some of its heavy elements that would fill the intergalactic medium around it. This would make sure that any stars that form from Orion's ashes will have the materials they need to make rocky planets and maybe even life. Astronomers can already see the earliest signs of that transition. High-resolution observations from the Hubble Space Telescope and JWST reveal faint arcs of compressed gas around Theta C, possibly shaped by its stellar wind colliding with the surrounding medium. These arcs may represent the early formation of a wind-blown bubble, a precursor structure often found around stars nearing the end of their lives. Within this bubble, the gas density is low, but the pressure is immense. When the final explosion comes, the shockwave will expand freely through this cavity before slamming into denser gas at its edges, producing a brilliant supernova remnant similar to the Crab Nebula or Cassiopeia A. Astrophysicists think that Theta C has less than 5 million years of steady burning left, but they don't know when it will die. In the big picture, that's not even a breath. There will be no quiet death when it goes. The supernova's light will quickly make Orion one of the brightest areas of the night sky. If it happened in our time, it would be visible from Earth during the day. Its radiation will spread through space, and the nebula's stars that are still alive will find themselves in a very different world. For close smaller stars like the Sun, it could mean the loss of rings and atmospheres. For gas clouds far away, it could cause the next wave of star births. The next part of Orion's story will begin when one star dies. The nebula's changing face. At first view, the Orion Nebula looks like it hasn't changed since ancient scientists first saw its faint glow. It looks like a jewel that has been hanging below Orion's belt. But new observations have shown something truly amazing. Orion is changing right in front of our eyes. The nebula's gas and dust aren't stuck in one place. They're always moving, changing the shape of the nebula in ways that can be seen in a human lifetime. Orion is one of the few places in the universe where scientists can watch the beginning of the universe happen in real time because it has life. For decades, the Orion Nebula was thought to be stable. The vast distance, roughly 1,344 light-years, made it seem static, its forms permanent. But beginning in the late 1990s, a series of long-term studies with the Hubble Space Telescope began to change that view. By comparing high-resolution images taken years apart, scientists discovered subtle yet measurable shifts in the positions of gas filaments, shock fronts, and knots of material. Some regions had moved by several arcseconds, corresponding to real velocities of tens of kilometers per second. The nebula's shape, once assumed to be fixed, was in fact flowing and evolving, driven by the combined winds and radiation of its thousands of young stars. One of the most dramatic examples of this movement comes from the Herbig-Haro objects, scattered throughout the nebula, glowing jets of gas ejected by newborn stars. When Hubble imaged these objects over a span of just a few years, astronomers noticed clear displacements. These jets weren't static structures, but fast-moving streams, shooting through the surrounding gas like cosmic bullets. Their changing positions provided the first direct evidence that Orion's internal landscape was shifting on human observable timescales. Some of these jets, such as HH202 and HH203, have visibly expanded and brightened since their discovery, proving that the nebula's activity is ongoing and dynamic. Further confirmation came from radio and infrared observatories like ALMA and JWST, which can peer through the dust that obscures much of Orion's structure. These instruments have revealed swirling flows of molecular gas spiraling outward from the trapezium cluster and the OMC1 core. In ALMA's data, astronomers can track these movements like weather systems, watching how stellar winds carve new cavities while radiation pressure sculpts edges into sharp arcs. The most active regions, such as the Orion bar and the BNKL outflow, show measurable expansion year by year. What once appeared as frozen beauty is, in truth, a scene in motion, constantly redrawn by forces both creative and destructive. The color of Orion is also changing, albeit slowly. The glow of the nebula comes from ionized hydrogen recombining with electrons, producing the iconic red H-alpha light. But as the ionization front expands, and as the balance between gas density and radiation shifts, the overall brightness fluctuates. Observations over the past few decades suggest small but consistent variations in emission intensity across certain regions, particularly near the Orion bar. These changes correspond to waves of increased or decreased ultraviolet flux from the trapezium stars, whose activity cycles may cause periodic fluctuations in the nebula's illumination. In other words, Orion's light pulses with the rhythm of its stars. The nebula's weather inside is even more appealing. Magnetic turbulence and shockwaves make pressure differences that move fronts of heavier gas across light years. As these fronts move, they push and change the shape of things around them like slow-motion shockwaves. Based on real observations, computer models of Orion's motion show that its most recognized features, like the bright inner hollow and the curved arcs near the trapezium, will look very different in just a few thousand years. They won't be recognizable in a million years. The Orion Nebula is not a still painting. It is a time-lapse picture of the universe being made, one moment at a time. What's truly mind-bending is that we're not just seeing Orion change. We're seeing it as it was 1,344 years ago. Because of the speed of light, the photons reaching our telescopes today left the nebula during the early Middle Ages. So even as we observe its motion, we're watching a delayed broadcast of the past. By combining these temporal and spatial shifts, astronomers can model how Orion appears not just now, but how it will appear in the future. These models predict that within the next few million years, the nebula's gas will continue expanding outward, eventually dispersing into the surrounding interstellar medium. The bright core will fade, leaving behind only the open cluster of stars, the skeletal remains of what was once a cosmic masterpiece. Cosmic sculptors, stellar winds and radiation pressure. The Orion Nebula's beautiful swirls and curves are not random. They were made by artists who can't be seen. It has very large stars that send out stellar winds and radiation pressure that shape the gas and dust into bridges of light, hollow spaces, and complex filaments. The bright center where the trapezium stars live, the dark pillars that hide suns that are still growing, and the wispy edges that sparkle with light make up Orion's shape. If the nebula is a painting, these forces are the paintbrushes that are always adding new strokes to the picture we see in the night sky. Stellar winds are streams of charged particles, mainly protons, electrons, and ions, ejected from a star's surface at supersonic speeds. For ordinary stars like the Sun, these winds are gentle, but for massive O-type and B-type stars like those in the trapezium cluster, they are hurricanes. Theta 1 Orionis C, The cluster's dominant star drives a wind traveling at over 2,000 kilometers per second, carrying away millions of tons of material every second. When that wind slams into the surrounding gas, it sweeps it aside, creating a vast bubble of ionized plasma. The Orion Nebula's central cavity, roughly 4 light-years wide, was carved by just such an outflow, hollowing the cloud and exposing the young stars within. Radiation pressure works alongside these winds, but in a subtler way. Every photon emitted by a hot star carries momentum. When that photon strikes a dust grain, it exerts a tiny push. Multiply that by the unimaginable number of photons pouring out of the trapezium cluster each second, and the result is a force strong enough to move mountains of interstellar material. Radiation pressure drives gas away from the stars, clearing cavities while compressing dense knots of matter at the nebula's edges. These compressed regions can become new birthplaces for stars, a process known as triggered star formation. In this way, the same energy that destroys one part of the cloud creates the conditions for another to bloom. Astronomers can see this sculpting in progress. The Orion bar, that razor-sharp strip of light separating the nebula's glowing interior from its darker outskirts, is one of the clearest examples. It marks the boundary where ultraviolet light from the trapezium's giants meets dense molecular gas. At that frontier, radiation pressure heats and erodes the surface, slowly peeling layers of material away like smoke from a flame. Behind the bar, shockwaves ripple through the gas, compressing it further and forming bright ridges and knots visible in infrared light. The result is a structure of exquisite detail, thin glowing edges and shadowed folds that reveal the constant tug-of-war between light and matter. Similar sculpting occurs across Orion's entire expanse. Pillars and globules, like those near the trapezium's outskirts, owe their shapes to the same interplay. As winds and radiation strip away the less dense material, the denser cores resist, standing as dark silhouettes against the bright background. These elephant trunks, as astronomers call them, often harbor embryonic stars within. Over time, they will either collapse into new suns or erode completely, releasing their contents into the nebula. Every one of Orion's delicate tendrils and glowing arcs is a frozen moment in this relentless battle, one that transforms destruction into creation again and again. Data from the Hubble Space Telescope and JWST show that the total kinetic energy of Orion's stellar winds equals that of billions of nuclear bombs detonating every second. Yet the nebula's gas is so diffuse that even such immense power sculpts rather than obliterates. Instead of violent explosions, we see gradual molding, erosion, compression, and re-illumination. The gas flows outward in waves, creating complex patterns of density and motion that radiate from the cluster's center. These outflows, interacting with magnetic fields and turbulence, produce the layered structure that makes Orion so captivating in high-resolution images. As the winds expand, they cool and slow, eventually mixing with the ambient interstellar medium. But even in their waning stages, they carry heavy elements, carbon, oxygen, nitrogen, forged inside the stars themselves. These materials seed the surrounding space, ensuring that when new clouds form, they will be enriched with the ingredients for rocky planets and organic molecules. In this sense, the sculpting isn't just visual, it's chemical. The very act of shaping the nebula spreads the building blocks of future worlds. Radiation pressure also leaves marks that last. It makes temperature and ionization variations that set the color palette for Orion. Hydrogen gives off a red glow, oxygen a greenish shimmer, and scattered light has blue lines. These colors come from the way photons interact with gas at different distances from their sources. These processes work together to give the nebula its layered look, with hot ionized areas moving into cooler molecular areas farther away. Some of these transitions are amazingly thin, only a few hundred astronomical units across, as shown by JWST's infrared images. This shows exactly how light can cut through the cosmic fog. Triggered star formation, a domino effect. The Orion Nebula is not just a single burst of starbirth frozen in time. It's a chain of events like a domino effect, where one generation of stars sets off the next. The starlight and stellar winds from each bright young sun squeeze the gas around it, starting new waves of collapse. This feedback loop makes the nebula into a live machine, an engine of star formation that has been going for millions of years and may keep going for millions more. Because other stars were born before them, the nebula's glow is not just a picture of stars that were born in the past. It's a picture of stars that are being born right now. Astronomers call this process triggered star formation, and Orion is its textbook example. The massive O and B-type stars at the nebula's core act as the spark. Their ultraviolet radiation ionizes and heats the surrounding gas, driving powerful shock fronts outward. When these shock fronts encounter cooler, denser molecular clouds, they compress them, increasing the local pressure until gravity takes over and the clouds collapse into new protostars. These newborn stars, in turn, begin to emit their own winds and light, sending new waves of compression outward. The result is a rolling pattern of creation, a cosmic relay race where each generation hands the baton to the next. The clearest evidence for this comes from the spatial structure of Orion's stellar population. Observations show that the oldest stars, roughly 5 million years old, lie farther from the current nebula, in regions like Orion OB1A and OB1b. Closer in, younger stars populate areas like OB1c, while the youngest of all, less than 1 million years old, reside within the Orion Nebula cluster itself. This arrangement forms a perfect timeline written across space, the trail of successive bursts of formation moving inward toward the present. The likely cause: earlier generations of massive stars blowing bubbles of hot gas that compress the surrounding cloud, triggering collapse in concentric waves. Each wave of creation literally carved the path for the next. At the micro level, JWST and ALMA have captured this process in exquisite detail. In regions like the Orion Bar and the OMC1 ridge, astronomers can see shock fronts where hot ionized gas meets cold molecular material. These boundaries, called photon-dominated regions, PDRs, are where the chemistry of star formation begins. As the shock wave travels, it sweeps up gas and dust into dense sheets, fragmenting them into knots that quickly become gravitationally unstable. Within these knots, new stars ignite, often surrounded by protoplanetary disks. It's a slow-motion chain reaction, energy from one set of stars giving birth to the next, step by step, across light years. This domino process doesn't just create stars, it organizes them. The resulting stellar hierarchy in Orion, clusters, subclusters, and associations, mirrors the waves of triggered formation. Large-scale feedback from the trapezium cluster sculpts the overall structure, while smaller-scale feedback within dense cores determines local clustering. The result is a pattern of interconnected stellar nurseries that all trace their lineage back to the same parent cloud. In many ways, Orion acts like a biological system, a self-replicating organism, where each generation's output shapes the conditions for its descendants. Even the Horsehead Nebula, located just south of Orion's belt, may owe its peculiar shape and star formation to this process. The intense radiation from nearby stars in Orion's OB1 complex has been eroding its edges, compressing gas within the dark pillar and igniting new protostars along its rim. This shows that Orion's influence extends far beyond the visible nebula. Its shockwaves are still seeding starbirth hundreds of light-years away. The entire Orion complex, from the Flame Nebula to Barnard's Loop, can thus be seen as a chain of successive generations, each born from the remains of the last. Triggered star formation also explains why Orion remains so active despite constant erosion. Normally, stellar feedback should disperse the gas, halting further collapse. But in Orion's case, that energy keeps recycling, blowing away some regions while compressing others. This balance sustains the nebula's life cycle, ensuring that even as old stars clear out cavities, new ones ignite at the edges. It's an elegant feedback loop of destruction and creation, perfectly tuned by gravity and pressure. Without it, Orion would have faded long ago. With it, the nebula continues to pulse with life, generation after generation. Orion's link to the Horsehead and Barnard's Loop The Orion Nebula is beautiful on its own. It looks like a hunter's sword, a bright pot of gas and new stars. But it's not a space island by itself. This is a small part of a much bigger structure that spans hundreds of light years and connects many stars. Along with the Horsehead Nebula, Barnard's Loop, the Flame Nebula, and other star nurseries, the Orion Nebula is just one bright knot in a much bigger web. This web is made up of strands of gas, shockwaves, and magnetic fields that connect all the objects in it. To fully understand Orion, we need to stop seeing it as a single cloud and instead see it as a live cell inside a galaxy. At the grandest scale, all these regions belong to the Orion Molecular Cloud Complex, one of the largest and most active star-forming regions in the Milky Way. This immense complex spans nearly 500 light-years and contains enough gas and dust to form hundreds of thousands of stars. It's divided into two main clouds, Orion A, where the Orion Nebula itself lies, and Orion B, home to the Horsehead and Flame nebulae near Orion's belt. Both are connected by long filaments of molecular hydrogen, invisible in visible light but glowing brightly in radio and infrared wavelengths. These filaments act like the veins of a giant cosmic organism, channeling material and energy between regions, feeding new generations of stars. The Orion Nebula sits in the lower part of this structure, embedded in Orion A, a vast river of gas that stretches southward like a luminous spine. Just north of it, along the belt, lies Orion B, dominated by the dark silhouette of the Horsehead Nebula. The Horsehead, one of the most iconic shapes in the night sky, is not a separate cloud, but a protruding clump of dense gas illuminated from behind by ultraviolet radiation from the bright star Sigma Orionis. The same radiation that lights up the Orion Nebula's interior is sculpting the Horsehead's edges, slowly eroding it over time. Observations show that the Horsehead's dense ridge is currently forming new stars within its shadowed interior, proof that it is part of the same ongoing chain of triggered star formation spreading outward from Orion's core. Wrapping around the entire constellation like a crimson halo lies Barnard's Loop, a colossal arc of glowing hydrogen gas nearly 300 light-years wide. To the naked eye under dark skies, it appears as a faint curved ribbon surrounding Orion's belt and sword. This structure is thought to be the remnant of a supernova, or series of supernovae that exploded a few million years ago, possibly the same ancient events that triggered the formation of the Orion Nebula itself. The loop's curvature and expansion rate fit perfectly with the idea that it's an outward-moving shell of ionized gas, created when massive stars from an earlier generation ended their lives in spectacular explosions. The shockwaves from those blasts would have compressed nearby molecular clouds, igniting the star-forming regions we see today. The links between these regions are not merely spatial, but dynamic. Energy from one part of the complex constantly affects the others. The massive stars in the Orion Nebula bathe the surrounding gas with radiation that extends far beyond its visible borders, influencing the ionization levels in both Orion B and Barnard's Loop. Conversely, the older shells of Barnard's Loop continue to press inward, maintaining pressure on the nebula's outer edges. In this way, the entire Orion complex behaves as a single, self-interacting system, a grand feedback loop of stellar birth, death, and rebirth. Each part drives the evolution of the others, ensuring that the cycle of creation never truly stops. Astronomers have mapped this vast web using radio telescopes like ALMA and the Nobayama Observatory, tracing carbon monoxide emissions that reveal the structure's cold molecular gas. The data show filamentary bridges connecting Orion A and B, some extending for tens of light years. Along these bridges, clusters of protostars and dense cores have been detected, stars forming along the connective tissue of the complex itself. The discovery proves that Orion's regions are not separate clouds coincidentally aligned along our line of sight, but physically linked structures participating in a synchronized process of evolution. Lessons for planetary formation. It's like going back in time to look into the Orion Nebula. You can see the beginning of star systems like ours as well as the beginning of star systems. One of the closest and best places to study how worlds start is Orion. There are disks of material around hundreds of young stars that will one day turn into planets, moons, and asteroids. These disks are made up of bright gas and dark dust. A live picture of what our solar system might have looked like in its first few million years can be seen in these protoplanetary rings, also called proplyds. They show both the hope and danger of planet formation, which is helped by cosmic dust, but could be stopped by the strong radiation from close big stars. The Hubble Space Telescope first uncovered these proplyds in the mid-1990s, small, dark silhouettes outlined against Orion's bright background, each centered on a newborn star. Dozens were soon catalogued, and later observations with ALMA and JWST revealed hundreds more. These disks vary in size, composition, and shape, but all share a common fate. They are caught in a delicate balance between creation and destruction. On one hand, gravity and accretion are pulling gas and dust inward, forming planets. On the other, intense ultraviolet radiation from the trapezium cluster's massive stars, especially Theta 1 Orionis C, is blasting them with energy strong enough to evaporate their outer layers. The smaller, fainter stars farther from the trapezium can quietly form stable disks where planets may grow undisturbed. But those born closer to the nebula's center face a harsher fate. Their disks glow brightly in infrared and radio light because they're being photoevaporated, literally boiled away by ultraviolet radiation. In these exposed systems, gas is stripped faster than gravity can gather it, cutting off the supply of material needed for gas giants like Jupiter. Only rocky planets close to the star might survive. This phenomenon, known as environmental suppression, helps explain why some planetary systems form differently depending on where they are born within a nebula. Orion proves that not all cosmic nurseries are equally kind to their children. The nearby proplyds, seen by Hubble, look almost like teardrops, disks with long comet-like tails pointing away from the trapezium stars. These tails are streams of ionized gas, visible evidence of the ongoing assault from ultraviolet light. JWST has now shown that even within these harsh conditions, some disks persist longer than expected. Dense inner regions seem to shield the material inside, allowing rocky cores to continue forming even as outer layers evaporate. This resilience hints that planets can still emerge even in the most extreme environments, perhaps smaller, denser, and closer to their suns, but planets nonetheless. The effects on planetary research are very big. In Orion, we can see all the different ways that young systems could end up. Some are safe in dark, dusty cocoons on the edges of the nebula where low-mass stars can slowly gather gas without being bothered. Others are close to radiation fronts and are forming and under attack. The variety of these conditions is similar to the variety of exoplanets found throughout the galaxy, ranging from small, hard worlds that are close together to huge, gas-filled planets that move far away safely. Orion is the missing piece. It gives us a clear look at how this kind of variety comes from different birth environments. Another key lesson from Orion is timing. The nebula's stars are only a few million years old, and yet planet formation is already well underway. ALMA's images reveal rings, gaps, and spiral patterns in several disks, clear signs of planets carving paths through gas and dust. This means that worlds begin forming almost immediately after their parent stars ignite, perhaps within hundreds of thousands of years. The classic idea of planet formation as a slow, leisurely process is being replaced by a view of rapid, dynamic assembly, a race between gravity-building planets and radiation trying to destroy them. Orion's disks are the finish line of that race, frozen in every stage of victory or loss. For our own solar system, Orion may represent a window into our origins. The isotopic composition of certain meteorites suggests that the early Sun was born in a cluster containing massive short-lived stars, much like the trapezium. Those stars likely went supernova within a few million years, injecting radioactive isotopes like aluminum-26 into the solar nebula. These isotopes heated early planetesimals, driving chemical differentiation that shaped the structure of planets. Orion shows this same dynamic environment in action today. massive stars enriching their neighbors' disks, creating diversity among developing worlds. The same violent radiation that threatens life's beginnings may also make complex planets possible. A mirror of the early solar system. Astronomers who study the Orion Nebula are not just looking at another star nursery, they may be seeing a mirror of where we came from. It's almost exactly like what models say happened where our Sun was born 4.6 billion years ago. A dense, high-radiation cluster full of big stars, strong winds, and shockwaves from supernovae. Orion isn't just a view into the future of the universe, it's also a look into the past of humanity. It's like a picture of our cosmic cradle before the Sun, Earth, and everything else we know existed. The key evidence begins with the chemical record found in meteorites, remnants of the early solar system that act as time capsules from our origin. Inside certain chondritic meteorites, scientists have detected short-lived radioactive isotopes like aluminum-26 and iron-60. These isotopes decay quickly, meaning they must have been injected into the solar nebula shortly before or during the Sun's formation. The only known sources for such isotopes are massive stars and supernovae. This points to one inevitable conclusion. Our solar system formed in close proximity to one or more giant stars, just like those now blazing in Orion's trapezium cluster. That same scenario is playing out in Orion today. The massive O-type stars, particularly Theta 1 Orionis C, flood their surroundings with ultraviolet light and stellar winds, heating, ionizing, and reshaping the gas around them. Meanwhile, hundreds of smaller stars, each with their own protoplanetary disks, orbit nearby. Some of those disks are being eroded by radiation, while others, shielded by dust, continue to form planets. This balance between destruction and creation, between chaos and opportunity, is precisely the kind of environment our Sun likely grew up in. Orion, then, is a living analogue of the solar system's earliest days, chaotic, luminous, and full of possibility. One of the strongest links between Orion and our past lies in the proplyds, or protoplanetary disks, first discovered by Hubble and now imaged in extraordinary detail by JWST. These disks, roughly the same size as our solar system, orbit young stars that are only a few million years old, the same age the Sun would have been when its planets began to form. Many of these disks show evidence of photoevaporation, their outer edges glowing as they're stripped by ultraviolet radiation. This process is thought to have occurred in our solar system as well. The outer gas was likely blown away early, preventing Jupiter and Saturn from growing much larger and helping shape the architecture of our planetary system. In Orion, we can literally watch this sculpting in progress, a living demonstration of the same forces that set the stage for Earth's eventual emergence. Another clue comes from the mix of materials found in both Orion and the solar system. Infrared and radio spectroscopy have detected water vapor, carbon monoxide, ammonia, and complex organic molecules throughout Orion's dense molecular clouds. These are the same compounds found in comets, meteorites, and the interstellar dust grains that seeded Earth's early oceans and atmosphere. The parallel is striking. Both our system and Orion are rich in carbon chemistry, suggesting that life's essential ingredients are not rare, but fundamental to star and planet formation itself. In other words, what happened here is not unique, it's universal. Even the architecture of the Orion Nebula cluster, a crowded core surrounded by expanding outer layers, resembles what simulations predict for the Sun's original environment. Our star likely formed within a compact group of several thousand siblings, many of which would have been similar to Orion's mix of massive O-type and smaller K and M-type stars. Over time, the cluster would have dispersed as stellar winds and supernovae cleared the gas, leaving the Sun and its planets to drift alone through the Milky Way. If this is correct, our solar system began not in isolation, but in the heart of a nebula very much like Orion's, bathed in radiation, shaped by nearby explosions and forged in cosmic company. There is also strong evidence that the collapse of the solar nebula may have begun with a supernova spark. A dead, huge star's shockwave may have squished a nearby molecular cloud, starting the Sun's formation and adding radioactive isotopes from meteorites at the same time. This chain of events is very similar to what scientists see in Barnard's Loop and the areas around it. These areas have a feedback system where old stars die and their remains start new ones. We can see this whole process in Orion, from the supernova shell spreading to the bright new stars building up around it. There is a good chance that our sun's birth followed the same pattern. The environment of Orion also helps explain one of the solar system's enduring mysteries, why it's so chemically diverse. The early solar nebula contained both hot, processed materials from near the young sun and cold, pristine ices from the outer regions. This mixing could only occur in a turbulent, radiation-rich environment where magnetic fields and shockwaves constantly stirred the gas. The Nebula in Motion, Proper Motion Studies. The Orion Nebula is moving, even though it looks like it's stuck in the sky at night. Its gas and stars are drifting, colliding, and growing in a slow dance of space that scientists can now measure. For hundreds of years, Orion seemed to last forever, a steady light under the hunter's belt. But very accurate tools have shown that every star and wisp of bright gas inside it is moving. The nebula isn't static, it's a live system that's changing. It's spreading out, losing mass, and changing into an open cluster that will one day float across the Milky Way as a ghost of what it used to be. This insight comes from a remarkable convergence of modern tools. The Hubble Space Telescope, the Atacama Large Millimeter Submillimeter Array, ALMA, and especially the Gaia mission, which has measured the exact positions and motions of billions of stars across the galaxy. With Gaia's micro-arc-second precision, astronomers can now track the proper motions, the tiny shifts in position over time, of stars inside the Orion Nebula Cluster, 1C. These movements, when projected backward and forward, tell the story of Orion's past, present, and future. The O1C is not a calm, gravitationally settled cluster, but a system in flux. Its thousands of stars move in slightly different directions, many at speeds of a few kilometers per second relative to one another. Some are being drawn inward by the cluster's collective gravity, while others are being pushed outward by radiation and gravitational encounters. Over time, this dynamic interplay will pull the nebula apart. Simulations suggest that within about 10 million years, the Orion Nebula will disperse entirely, its gas gone and its stars scattered into a loose association drifting along the Milky Way's Orion arm. There is a story of gravity chaos at the heart of this action. The nebula's main source of energy comes from the trapezium cluster, which is a close-knit group of heavy O and B-type stars dancing in space. Because they are so close and have so much mass, they create strong tides that constantly move nearby stars. Gaia's data show that a number of young stars in the cluster are being thrown out at very high speeds. These stars are being thrown away by close encounters that are like heavenly slingshots. A star called the Becklin-Neugebauer object is one of these stars that has already left the cloud and is speeding through space at over 100 kilometers per second. Each release event changes the cluster's balance in a small way, making it less stable over time. The nebula's gas and dust are expanding outward under the combined influence of stellar winds and radiation pressure. Observations of emission lines from hydrogen and oxygen reveal that the gas flows at speeds between 10 and 30 kilometers per second, forming expanding shells around the trapezium. These flows are not uniform. They form arcs, filaments, and bubbles where winds collide. Over time, these bubbles merge and grow, eventually rupturing the nebula's outer layers and releasing its gas into the surrounding interstellar medium. In essence, Orion is exhaling, slowly releasing the material that once nourished its stars. Proper motion studies also show Orion's interesting three-dimensional structure, which can't be seen in flat pictures. Early scientists thought the nebula was a flat sheet of gas, but it's actually a stacked, uneven bubble with stars spread out at different depths. Gaia's parallax data show that the trapezium cluster is a little closer to us than the molecular cloud around it. This means that the winds from the cluster have already blown a hole toward our line of sight. Visible light shows that the bright gas makes up the near wall of this hole, which is lit from behind. It's kind of like looking into a hollowed-out bubble. The inside shines like etched glass against the dark outside. The motion of stars within Orion is not random. It reveals patterns that trace the nebula's history. Some groups of stars move together in tight formations, remnants of smaller subclusters that merged to form the ONC. Others move in diverging streams, suggesting they were expelled during earlier dynamical interactions. These details allow astronomers to reconstruct Orion's formation step by step, collapsing filaments forming small clusters, clusters merging into one massive hub, and gravitational turbulence slowly tearing it apart again. It's a continuous cycle of assembly and dispersal, the same process that builds and dissolves stellar groups throughout the Milky Way. Even the gas velocities tell a story. ALMA has mapped the motions of molecular gas in Orion with exquisite precision, revealing rippling waves and expanding fronts that correspond to shockwaves from stellar outflows and past collisions. In some places, the gas moves toward us. In others, it recedes, a complex three-dimensional breathing motion. The Orion Nebula, in this sense, behaves almost like a living organism, inhaling and exhaling energy through its vast network of filaments. As the massive stars at its core evolve and explode as supernovae, the energy from those blasts will accelerate the dispersal. The resulting superbubble, combining remnants of Orion's gas with older shells like Barnard's Loop, will eventually merge with the larger Orion Eridanus superbubble. When that happens, the Orion Nebula will cease to exist as a distinct object. What remains will be a young open cluster, a few thousand stars drifting together through the galaxy, their past written only in their shared motion and chemical fingerprints. When Orion will fade. The Orion Nebula, which shines faintly below the Hunter's Belt, is seen by millions of people every night. It is a sign that the world is alive and making new things. But in the grand scheme of things, what we see is temporary. Even though it is very beautiful, the Orion Nebula is only temporary. It is a bright explosion of creation that will go away in 10 million years. In terms of stars and galaxies, that seems very far away, but it's really just the blink of an eye. The things that make Orion shine now are the same things that will make sure it goes away in the end. Right now, the nebula glows because the powerful ultraviolet radiation from the trapezium cluster, especially the massive O-type star Theta 1 Orionis C, is ionizing the surrounding hydrogen gas. This light gives Orion its familiar pink and crimson hues, the color of recombining hydrogen atoms. But as the cluster's massive stars age, that radiation will wane. Within a few million years, Theta C and its peers will die in violent supernova explosions, their light briefly outshining entire galaxies before fading into silence. When they go, the engine that keeps the nebula glowing will go with them. Even before that, the nebula is already fading, slowly, imperceptibly to human eyes, but unmistakably in astronomical data. The powerful stellar winds from the trapezium stars continue to blow gas outward, thinning the nebula's inner regions. Observations show that the cavity around the trapezium is expanding at roughly 10 to 20 kilometers per second, pushing gas into the surrounding molecular cloud. Over time, this expansion will rupture the nebula's boundaries completely, allowing ultraviolet radiation to escape into open space rather than bounce around within. As that happens, the nebula's once bright glow will dim. Its filaments and pillars will unravel, and the complex architecture that telescopes now capture in vivid detail will dissolve into diffuse starlight. The timeline of this fading is written in the nebula's structure. On the outer edges, the gas density is already dropping as winds and radiation pressure drive material away. The iconic Orion bar, once a sharp boundary between ionized and molecular gas, will erode as ultraviolet light eats deeper into the cloud. The OMC-1 core, where stars are still forming, will exhaust its supply of dense material within a few million years. Without gas to feed it, star formation will cease. By then, Orion will no longer be a stellar nursery, but a young open cluster, surrounded by a faint, expanding shell of leftover material, the last echo of its former brilliance. Though the nebula will die, it will not be the end of its story. Instead, it will change. The gas being pushed out today will fill the space around us with heavy elements that were made in stars in the past. The interstellar medium will become richer for the next cycle of creation as carbon, oxygen, silicon, and iron move through it. These are all important elements for planets and life. The shorter-lived stars in the cluster will stay put and circle around each other as a loose family for hundreds of millions of years. Then, the galaxy's tides will pull them apart. Some will carry planets, and others may finally form their own worlds where people can live. The things that Orion leaves behind will be more important than its light. We can already see glimpses of what this future looks like in older clusters. The Pleiades in Taurus, for example, is an open cluster roughly 100 million years old, the evolutionary descendant of a nebula much like Orion's. Once, it too was wrapped in glowing gas. Now, only the stars remain, faintly illuminating the dust they once formed from. Orion will follow the same path. In about 5 to 10 million years, the last of its gas will dissipate. In 50 million, its remaining stars will spread so far apart that the cluster will fade from view entirely. The hunter's sword will hang empty in the sky, the glow gone, replaced by the quiet shimmer of individual suns. Even from Earth, our descendants will one day witness Orion's disappearance. The nebula's light is already 1,344 years old when it reaches us, but in astronomical time, that's nothing. In a few tens of millennia, the bright inner regions may appear dimmer through telescopes, its delicate filaments harder to trace. Over eons, as the stars move and the gas disperses, the very pattern of Orion's constellation will shift. The hunter's belt, the sword, and the bright glow below, all will change as the stars continue their long march across the sky. The Orion Nebula, once the most studied and admired stellar nursery in human history, will become a faint ghost of hydrogen stretched across the Milky Way. The legacy of Orion. When the Orion Nebula finally goes away, there will be more than just stars and dust left behind. There will be a model for how the universe was made. No other spot in the sky has taught people more about how stars get their sparks, how planets are made, and how chaos can turn into order. Its memory will live on for a long time, not only in the science record, but also in the stars it left behind and the stories they continue to tell across the sky. The Orion Nebula has been our nearest classroom for understanding the entire life cycle of the cosmos. From the gravitational collapse of cold hydrogen to the ignition of massive stars, from the formation of protoplanetary disks to the chemical seeding of future worlds, every stage of cosmic evolution is captured within its light. It is both a beginning and an ending, a place where destruction and creation coexist. Astronomers have studied thousands of nebulae across the Milky Way, but Orion, at only 1,344 light-years away, has given us a front-row seat to the machinery of the universe at work. The nebula's greatest contribution may be its role as the Rosetta Stone of star formation. Through telescopes like Hubble, Spitzer, and JWST, scientists have mapped how gas collapses into stars, how radiation shapes the resulting clouds, and how magnetic fields, shockwaves, and turbulence all interact to create order from chaos. The data from Orion has refined our understanding of how the Sun and its siblings were born, providing the most detailed models ever made of stellar nurseries. Every glowing arc and pillar in Orion tells a story about how gravity and light negotiate the terms of creation, and those stories now underpin nearly every modern theory of astrophysics. When the nebula finally disperses, its stellar children will continue the story. Thousands of young stars born within Orion will drift outward over millions of years, scattering through the Milky Way's Orion arm. Some will carry planets, others will merge into new clusters, or pass close to existing systems, influencing the galactic landscape. Their light will still shine long after the nebula's gas has faded, a quiet reminder of the furnace that forged them. In this way, Orion's true monument will not be its nebula, but its descendants, suns that will one day host planets, perhaps even life, that trace their ancestry back to this single glowing cloud. The nebula has also transformed our technology and imagination. From the first telescopic drawings by Charles Messier in the 18th century to JWST's cutting-edge infrared mosaics, Orion has pushed human vision to its limits. It has inspired painters, poets, and physicists alike, serving as a meeting point between art and science. The images of Orion, its swirls of rose and teal, its radiant heart, have become symbols of exploration and curiosity, reminders that beauty and knowledge are intertwined in the same cosmic light. Scientifically, Orion's influence extends even further. Studies of its gas composition have revealed how elements cycle through galaxies. Its X-ray and infrared emissions have helped calibrate instruments and test astrophysical models. Every new space telescope has, at some point, turned toward Orion to test its precision, because the nebula is both complex and familiar, a perfect proving ground. In this sense, Orion isn't just a subject of study. It's the standard by which we measure the universe itself. The Orion Nebula is not a still image. It is a beating heart of creation that shows that even stars are born from chaos, battle, and light. If you liked this trip through the universe's most beautiful nursery, please like the video, subscribe for more cosmic stories, and watch the next exploration, which is now loading on your screen.